26,000 light-years from here, at the very center of the galaxy, there is a ring of light. It is not a large ring, as the galaxy measures things. Seen from Earth, it spans 52 microarcseconds, an angle so narrow that it is smaller than the apparent size of an orange resting on the surface of the moon. And yet within that ring, the entire gravitational weight of 4 million suns is folded into a volume no larger than the space between the sun and the planets that circle it closest. The ring glows orange. It glows because the gas falling toward the center has been heated past any ordinary temperature, heated to millions of degrees, compressed and stirred by tidal forces so extreme that matter ceases to behave in any way familiar to the world of cold and slow things. The glow is not fire in the way a candle burns. It is the light of plasma, of atoms stripped bare of their electrons, spiraling inward along magnetic field lines so tangled and dense that no single particle travels in a straight line for long. At the center of the ring is shadow. The shadow is real. It is the place from which no light returns, not because it is dark in the ordinary sense, but because space itself curves so sharply there that even light traveling at the only speed it knows cannot find a way back out. This is Sagittarius A star, the supermassive black hole at the heart of the Milky Way. In 2022, a collaboration of radio observatories spread across the surface of the Earth, linked together until they formed an instrument roughly the size of the planet, captured the first direct image of its glowing surrounding ring, that faint orange circle, just 52 microarcseconds wide, as seen from here. It had been suspected for decades. The mass had been calculated from the motions of stars orbiting close around it. But the image was the confirmation, the shadow made visible, the weight of 4 million suns given shape at last. Spend a moment with that shadow before passing outward. It sits at the crossing point of every large-scale structure this galaxy possesses. Spiral arms trace back to it. The bar of the galaxy pivots near it. The great lobes of ancient energy that rise above and below the disk have their origin there. Everything in the galaxy is in some slow sense organized around the fact of what sits at the center, and what sits there does not announce itself. It simply holds with a patience that has no equivalent in the human experience of time. The stars nearest to it move at speeds that make the word orbit feel inadequate. Among them are the S-stars, young, massive, blazing with blue-white light, which sweep around Square A star in tight elliptical paths that carry them within fractions of a light-year of the central mass. The star known as S2 is among the most closely watched. Its orbit takes only about 16 years to complete. 16 years, a timescale a person can hold in memory, brief enough to be personal, yet the path S2 traces around the galactic center is one of the most extreme journeys any known object makes, carrying it in close and then swinging it back out at several percent of the speed of light, its position shifting visibly between observations made only months apart. The paradox of these stars is quiet but deep. They are young. They are massive, ONB-type stars, only a few million years old, and they orbit within a fraction of a light-year of a gravitational force so extreme that the tidal stresses at that distance should tear apart any cloud of gas and dust before it can collapse into a star. The region is too violent, too sheared by tidal forces, too threaded by intense magnetic fields for ordinary star formation to proceed. And yet there they are, burning, young, orbiting close. How they came to be there, whether they formed elsewhere and migrated inward, Whether the disk of gas around the central mass produced them under conditions not yet understood remains one of the genuine open questions in the physics of galactic centers. They are called the paradox of youth, these brilliant stars orbiting an object that should not permit them to exist so near. Watch S2 for a moment. It moves so fast at closest approach that the color of its light shifts measurably toward the red, a gravitational redshift caused by the deepening of space around 4 million solar masses pressed into too small a place. The shift is small. It takes careful instruments to separate it from the Doppler motion of the star itself. But it is there, a real physical effect, one prediction of general relativity made real in the light of a single star sweeping around the invisible. The light from S2, when it arrives at Earth, carries the signature of the mass it swings around. The mass writes itself into the spectrum. Farther out from that central shadow, though still close, still within the innermost few light years, there is a ring of rotating gas and dust. It turns slowly around Skygra, a star at a distance of just a few light years, like a collar around the throat of the galaxy's deepest gravity. It is called the circumnuclear disk. It is not a simple structure. It is clumpy and uneven, shaped partly by the radiation pouring from the cluster of massive stars within it, and partly by the tidal forces of the black hole itself. The inner edge of this disk sits close enough to the central mass that material stripped from it occasionally flows inward, feeding the black hole in brief episodes of activity. The disk turns. It has turned for a very long time. The gas within it is cold by the standards of the hot plasma nearer the center, though still warm by the standards of ordinary molecular clouds, and it glows faintly in infrared and radio wavelengths that no human eye was built to see. The circumnuclear disk marks a kind of threshold. Inside it, physics operates under conditions that exist nowhere else in the ordinary galaxy. Tidal forces that shred, radiation fields that ionize, magnetic fields that resist collapse. Outside it, moving outward through the first few dozen light years, around the galactic center, conditions begin to trend toward what might loosely be called ordinary, though they are still far from it. Beyond the circumnuclear disk, extending outward to roughly 1,000 light years from the galactic center, lies a region known as the central molecular zone. It is not a place that photographs beautifully in visible light. Dense clouds of gas and dust scatter and absorb the optical wavelengths, and the view through a normal telescope toward the center of the Milky Way is one of obscuration, dark lanes, and dust curtains hanging in front of the center. But in radio wavelengths, in infrared, the structure of this region opens up. There is gas here, an enormous amount of gas, somewhere between 50 and 60 million solar masses of cold molecular hydrogen, threaded with carbon monoxide and denser tracers, pooled in the inner 1,000 light years of the galaxy, in quantities that ought to be producing stars at a rate far exceeding what is actually observed. The paradox of the central molecular zone is a quiet one, not dramatic to the eye, but deep to the mind. Density alone should be enough to trigger star formation. Clouds of gas that become dense enough, cold enough, inevitably collapse under their own gravity, and where gas collapses, stars form. That is the rule almost everywhere in the disk of the galaxy, but in the central molecular zone, the rule breaks down. The gas is dense, yes, but it is also threaded by magnetic fields far stronger than those in the outer disk. It is stirred by turbulence far more vigorous than anything in the quiet spiral arms. The tidal forces of the galactic potential, the combined gravitational pull of the bar, the bulge, the central mass, are strong enough to shear apart clouds before they can concentrate sufficiently. The gas accumulates, it churns, and it does not, for the most part, collapse into stars the way the same density of gas would collapse in a quieter neighborhood. This turbulence is visible in the velocity structure of the gas. Radio surveys of the central molecular zone show gas at many different velocities along the same line of sight, evidence that the clouds are not moving in gentle circular orbits, but are being pushed and pulled into complex overlapping paths by the gravitational influence of the bar, the central mass, and each other. Some gas streams inward along the bar and falls into the central molecular zone from larger radii. Some material gets caught in the orbit, families imposed by the bar's rotating potential, and loops around the center in elongated trajectories. The result is a constantly stirred, never quite settled sea of cold gas, dense enough to hide entire stellar nurseries on its far side, turbulent enough to resist the collapse into stars that its density would otherwise demand. Let the scale settle in for a moment. The central molecular zone, this one turbulent sea of cold molecular gas, spans 1,000 light-years. The distance from the Sun to the nearest star, Proxima Centauri, is just over 4 light-years. The central molecular zone stretches outward from the galactic center for 250 times that distance in every direction. It is not small, and it sits entirely within the structure of the bar, which extends outward for another 7,000 or 8,000 light-years beyond even that. The bar, this is where the galaxy declares itself something other than a simple spiral. Looking at other galaxies seen face-on from a distance, the beautiful oblique photographs taken by large telescopes of galaxies tens of millions of light-years away, it is easy to see which ones carry a bar. The bar is a linear concentration of stars, a thick bright stripe crossing the nucleus, from which the spiral arms extend at each end. The bar of the Milky Way runs from one side of the galactic center to the other, and its half-length, the distance from center to tip, is somewhere between 14,000 and 16,000 light-years. It is oriented at an angle to the line connecting the Sun to the galactic center, tilted by roughly 25 to 45 degrees away from that line, making it impossible to see in a simple direct view, but traceable in surveys of stars, gas, and dust across the inner galaxy. The bar rotates, not as a solid object rotates, the way a spinning top or a wheel turns, all parts at the same angular speed. Rather, the bar is a structure that persists through the coherent orbits of billions of stars, which naturally settle into elongated, aligned paths that collectively produce the barred shape. The bar turns at what is called its pattern speed, a rotation rate that is different from the orbital velocity of any individual star within it. Stars drift in and out of the bar structure over long timescales. The bar is more like a wave through a crowd than a crowd moving together. One of the key roles the bar plays in the life of the galaxy is in funneling material toward the center. Gas clouds in the inner galaxy are deflected by the bar's gravitational potential and driven along the bar's length toward the central molecular zone. This feeding mechanism has been active for billions of years, channeling raw material inward and keeping the innermost regions of the galaxy supplied with the molecular gas from which stars, however slowly and reluctantly, eventually form. The bar is not simply a decorative feature of the galaxy's structure. It is a transport mechanism, moving mass from the middle distances of the inner disk toward the dense and turbulent heart. The bar also classifies the Milky Way in the taxonomy that astronomers use to sort and compare galaxies. A galaxy with a bar is assigned a B in the Hubble classification scheme, and the Milky Way falls into the type known as SBBC, a barred spiral of intermediate winding with moderately open arms. It sits among a common and well-studied class of galaxies, not a peculiarity, not an extreme case. It is ordinary in the way that most large spiral galaxies are ordinary, which means that everything described here, the black hole, the turbulent central gas, the ancient bar, is repeated in broadly similar form across hundreds of billions of other large galaxies in the observable universe. There is something restful in that ordinariness. The galaxy, with all the complexity of its center, is an example of a recurring pattern, a form that the universe has arrived at again and again across its full breadth. Now hold the image of the bar and set it against the central molecular zone nested within it. The bar turns slowly, sweeping its gravitational influence around the inner galaxy. The central molecular zone churns within, a turbulent sea of cold gas that the bar feeds and stirs. And at the very center, at the crossing point of all this structure, Sagittarius A star sits and holds 4 million solar masses, a shadow ringed by orange plasma, a gravitational anchor around which everything else is organized, at least in these innermost 1,000 light years. Consider now the S2 star in its orbit once more, a brief orbit, 16 years, the length of a childhood, sweeping in close at several percent of light speed, bending the wavelengths of its own emitted light as it does so, and then swinging back out. In that inward pass, for a few months, CES2 is the fastest known star with a well-measured orbit, and then it recedes, and the next orbit begins, and the central shadow continues, unchanged, unmoved, 4 million solar masses waiting in the quiet at the center. Above and below all of this, above and below the plane of the galaxy, extending outward far beyond the central molecular zone and the bar and even the spiral arms, there are two vast lobes of invisible light. They cannot be seen with the naked eye, nor with any optical telescope. They are visible only in the gamma ray part of the spectrum, and in X-rays wavelengths far beyond what human eyes were made to detect. But they are real, and they are enormous. Each lobe reaches approximately 25,000 light-years from the galactic plane, one rising above, one descending below, their combined extent spanning roughly 50,000 light-years from tip to tip. They are called the Fermi bubbles, named after the gamma-ray telescope, whose survey of the sky first revealed their structure in 2010. The Fermi bubbles are not gradual. This is what marks them as significant among all the diffuse, cloud-like structures in the galaxy's extended environment. Their edges are sharp. In a structure this large, 25,000 light-years tall, a sharp edge means a specific origin. Diffuse processes, slow, steady leaking of gas, gradual magnetic inflation, the accumulated pressure of countless supernovae over billions of years, produce features with soft, uncertain boundaries. The sharp edges of the Fermi bubbles point toward a single episode, or a brief sequence of episodes, of violent energy release at the galactic center, an outburst concentrated in time rather than spread across it. The best current picture is that between 1 and 4 million years ago, the galactic center experienced a period of intense activity. Either Sagittarius A star consumed a large amount of mass in a relatively brief period, brief in galactic terms, perhaps 100,000 years or so, releasing an enormous burst of energy that drove material outward from the plane at high speed, or a concentrated episode of star formation and supernova activity near the galactic center injected enough energy to blow material outward into the halo. The distinction between these two possibilities has not yet been settled. The Fermi bubbles themselves do not carry enough information, at least not yet, to uniquely determine which process produced them, though each interpretation leaves slightly different signatures that ongoing observations continue to refine. What can be said is that the bubbles exist that they are large and that they are still expanding, slowly, at speeds that are high by human standards, but slow in the context of the distances involved. The edges of the Fermi bubbles continue to push outward into the surrounding halo gas. The hot plasma within them glows in gamma ray and X-ray light. The sharp boundary at their edges is a contact surface between the hot interior gas and the cooler ambient material of the galactic halo beyond. This boundary is not permanent. Eventually, over millions more years, the bubbles will continue to expand and thin, their edges growing less sharp, their interior gas cooling and mixing with the surrounding halo medium until what remains of them is only a faint enrichment of the halo with slightly hotter, slightly differently magnetized gas, the last fading signal of an event that 4 million years ago briefly lit the galaxy's center from within. 4 million years ago is, in the context of the universe, recent. The universe itself is close to 14 billion years old. 4 million years ago, early members of the genus Homo were walking on the African savanna. The event that inflated the Fermi bubbles happened so recently, in deep time terms, that the light from it has not yet had time to reach the nearest galaxies of the local group. The bubbles are still expanding. They are a current event in the framework the galaxy uses for time. Imagine them from outside. Imagine the Milky Way disk, thin, luminous, a great flat spiral seen obliquely from above, and rising from its center, two lobes extending above and below, each one 25,000 light-years long, glowing not in visible light, but in the cold blue shimmer of X-rays, and the faint hard glow of gamma rays, their edges traced like the outline of a pair of slowly inflating spheres, pressed up against each other at the galactic midplane. The disk continues to turn beneath them, stars orbiting in their slow circles, spiral arms tracing their logarithmic curves outward, all of it unaware in any meaningful sense of the vast architecture of high-energy plasma hanging in the halo above and below. The bubbles do not disturb the disk's ordinary operations. They are too far from the plane, too rarefied, too diffuse in their energy per unit volume to alter the lives of the stars and gas clouds and star-forming regions going about their ancient routines in the thin disk far below. But they are there, and their existence changes the character of the galactic center in the mind. The core of the Milky Way is not simply a dense, ancient, turbulent concentration of gas and stars and a single massive black hole. It is a place that has erupted, recently, violently enough to push visible, or rather gamma-ray visible, structures 25,000 light-years into the halo in both directions. Whatever happened 4 million years ago was the largest single release of energy in recent galactic history, and its signature is still propagating outward through the halo at this moment. Return, for a moment, to the ring, 52 microarcseconds, an orange glowing torus of superheated plasma, a shadow at its center. This was the image captured by a planet-sized radio telescope in 2022, the first direct view of the environment around a supermassive black hole at the center of our own galaxy. The ring is small in angular size, smaller than any structure ever resolved before in the radio sky, requiring baseline distances across the entire surface of the Earth to achieve the resolution needed to separate it from the surrounding emission. Yet the object it images is one of the most massive single structures in the galaxy, 4 million solar masses, the mass of 4 million entire stars, each one larger than the Sun by any ordinary measure, compressed into a region through which light cannot escape. The paradox of size and scale runs through everything at the galactic center. The smallest angular structure conceals the largest local mass. The most violent region in the galaxy has been relatively quiet for most of its history, generating the Fermi bubbles in one recent outburst and then settling back into a dim, low luminosity state that is unusual even among black holes of its size. The youngest stars in the innermost parsec exist where theory suggests no young stars should exist. The densest gas reservoir in the galaxy forms far fewer stars than its density implies it should. At every scale, the galactic center presents the appearance of something exceptional, behaving unexpectedly, something that does not quite follow the rules that describe the rest of the disk, and yet it endures. Sagittarius A star has sat at the center of the galaxy for billions of years, through the accretion of smaller galaxies, through the slow grinding of billions of orbits, through whatever event inflated the Fermi bubbles and then subsided. The bar has rotated across its billions of years. The central molecular zone has churned and slowly, reluctantly, formed some of its stars. The C-stars have swept their tight orbits around the central mass thousands of times since the event that created the Fermi bubbles. All of it has continued. All of it continues now, at this moment, 26,000 light years from the quiet room in which the sky outside is dark and the air is still. Think of the circumnuclear disk, that slow rotating collar of gas and dust just a few light years across, turning around the gravitational center. It glows faintly in infrared. It has been turning for a very long time. The inner edge faces the full radiation and tidal environment of the central parsec, and yet the disk persists, replenished slowly by gas falling inward from the central molecular zone, feeding in small amounts the central engine it circles. The disk turns, the black hole holds. The S-stars sweep their brief, brilliant orbits. The central molecular zone churns in the dark, slowly, reluctantly, making stars. And far above, far below, the Fermi bubbles expand outward, one slow centimeter at a time, into the halo. Their edges press gently against the surrounding medium. The plasma within them cools by a tiny fraction each year. The gamma-ray glow dims imperceptibly. The sharp edges, so diagnostic of a single concentrated event, will become less sharp with time, the contact surface diffusing over millions of years until the memory of the outburst is spread too thin to read clearly. But not yet, for now the edges are still sharp. The outburst has not yet fully dissolved into the halo. The event is still, in the deep time of the galaxy, recent. There is a quality to the galactic center in the mind's image of it, in the way the facts of it organize themselves, that is not quite like anything in the outer disk. It is not simply the extremity of the physics, though the physics are extreme. It is the density of history. The central molecular zone contains gas that has been cycling through the innermost regions of the galaxy for billions of years, driven inward by the bar, stirred by turbulence, slowly converted into stars that live brief, violent lives and return their material to the surrounding gas. The C-stars, paradoxically young, may have formed from gas that has been cycling through the galactic center for longer than the solar system has existed. The black hole itself grew to its current mass through billions of years of accretion, slow feeding, brief violent episodes, the accumulated infall of enormous amounts of gas, and the occasional passage of whole molecular clouds, too close to the central mass to survive. 4 million solar masses did not assemble overnight, and the Fermi bubbles rising above and below the plane of the galaxy, their sharp edges slowly expanding, their interiors glowing in wavelengths too high energy for the eye to register, are the most recent and visible record of that long history. They are the signature of an episode that the galactic center may have experienced many times before, leaving no comparably preserved record. The halo holds the memory of previous outbursts as faint chemical and thermal enrichments, traces too diffuse to distinguish cleanly from the ambient halo medium. Only this most recent event is preserved clearly enough in the sharp edges of the bubbles to be read at all. The galaxy has been erupting at its center from time to time throughout its history, and between eruptions it has sat quietly. The black hole surrounded by its dim ring of infalling gas, the S-stars orbiting, the central molecular zone churning in the dark. The quiet is not absence. The quiet is the condition within which the next episode accumulates, slowly, until the mass of gas and dust and cold molecular clouds falling toward the center tips some balance, and the galactic center becomes briefly something different, bright, active, driving material out into the halo at speeds that persist for millions of years in the expanding geometry of the Fermi bubbles. The bubbles are still expanding now. They are expanding at this moment, while the dark sky outside is quiet, while the air in the room is still, and the sounds of the ordinary world have settled into something small and far away. 25,000 light years above the galactic plane, the upper lobe of the Fermi bubbles pushes outward into the halo. One slow arc of compressed hot plasma pressing against the cooler gas beyond its edge. 25,000 light years below the plane, the lower lobe does the same. The galaxy turns beneath them, all its spiral arms and its bar and its millions of star-forming regions and its hundreds of billions of individual stars, all of it unaware of the two great lobes of ancient energy rising silently above and below. At the very center, the orange ring glows. The shadow at the center is still. The S-stars continue their brief, tight orbits. The circumnuclear disk turns. The central molecular zone churns in cold molecular dark. The bar rotates its slow pattern, feeding gas inward, organizing the orbits of billions of stars along its length, classifying this galaxy among the barred spirals, common, ordinary, repeating, that fill the observable universe. All of it turns. All of it has been turning for longer than the solar system has existed. All of it will continue turning after any record of this moment has dissolved into whatever the universe eventually becomes. The galactic center does not require observation to persist. It does not require understanding to hold its 4 million solar masses in place. It simply continues, as it has continued, quietly and without announcement, at the center of the long, slow turning of everything that surrounds it. The Fermi bubbles rise. They expand outward into the dark halo. Their edges are sharp. Their glow, invisible to the naked eye, continues to press outward at a pace too slow to perceive across any human timescale. The event that made them is 4 million years old, and its geometry is still growing, still widening, still pushing the quiet halo gas aside with the patient, unhurried pressure of an ancient outburst that has not yet finished moving through the dark. On a dark summer night, far from any city, the sky above the southern horizon thickens and brightens in a way that no single star can account for. It is not a point of light. It is a softness, a diffuse and gentle luminosity, gathering in the direction of Sagittarius, pooling between the constellations like something spilled slowly and left to glow. The eye cannot resolve it into parts. It appears as a single continuous brightening, a low, warm haze of accumulated light, and it has been there above every clear southern horizon since long before anyone thought to explain it. That glow is not young. The stars packed within it are not like the bright, hot, newly minted stars that trace the arms of the galaxy. These are old stars. Most of them formed when the universe was less than a quarter of its present age, in an era of violent, rapid stellar assembly that built more stars in a single billion years than the galaxy has managed in the 10 billion years since. By the time the solar system existed, many of these stars had already been burning for longer than the solar system has now existed. They predate the Earth by a margin the mind cannot comfortably hold, and yet their light arrives at the eye on a warm evening with no sense of urgency, as still and unhurried as any other light crossing any other distance. What that soft glow marks is the galactic bulge, a dense, swollen region of ancient stars surrounding the galaxy's gravitational center, extending outward in every direction to a radius of roughly 10,000 light years. It is not a disk. It does not lie flat. It billows outward from the center in all directions, thicker above and below the plane of the galaxy than the disk itself, so that seen from the outside, it would resolve into something more like a knot or a thickening at the middle of the galaxy's stem. Within that volume, stars are packed far more densely than they are here, near the sun. The spaces between them are still enormous by any earthly standard, but by galactic standards, the bulge is a crowd, a compression, a place where the galaxy's first energies were most intensely concentrated. Most of those stars are more than 10 billion years old. A few are as old as 12 or 13 billion years, formed within the first few 100 million years after the Big Bang, in a cosmos still new enough that heavy elements, iron, silicon, calcium, the materials of planets and bones, barely existed yet. They formed from gas that was almost entirely hydrogen and helium, lit only by the first generation of massive stars that had already lived and died before the sun was imagined, and they have been burning steadily and quietly ever since. They have watched the spiral arms form and reform. They were old before the sun ignited. They will still be burning, slowly and dimly, long after the sun is gone. The word for all of this is fossil, not in the sense of something dead and preserved in stone, but in the sense of something that retains the imprint of an earlier world. The bulge is a fossil record of the Milky Way's first epoch, when it was not yet the galaxy it became, when it was still assembling itself from mergers and gas and the gravitational collapse of dense primordial clouds. The stars that formed then did not simply accumulate and wait. They built the foundation on which everything later rested. They enriched the surrounding gas with the first heavy elements, set the gravitational conditions for the disk that would eventually form around them, and settled into the stable and nearly unchanging arrangement they still occupy today. When the eye rests on that soft glow above the southern horizon, it is touching that foundation. Within the bulge, the arrangement of stars is not simple. Early maps made in visible light showed relatively little, because the bulge lies behind enormous columns of interstellar dust that absorb and scatter optical light before it can travel the full 26,000 light-years to the solar system. But infrared light, with its longer wavelengths, passes through dust more easily, and when infrared surveys began to map the bulge with care and depth, what they found was not a smooth and featureless sphere. The distribution of stars was not symmetric in the way a simple, ancient spherical structure would suggest. Instead, it had a shape. The shape became clearest when astronomers cataloged a particular class of stars known as red clump giants, stars at a specific and predictable stage of their evolution, all burning at nearly the same intrinsic brightness, which makes them useful as measuring rods across the bulge. When the distances to tens of thousands of these stars were calculated and mapped, they did not fall evenly throughout the bulge. They clustered in two distinct concentrations, one slightly closer and one slightly farther than a simple sphere would predict, offset above and below the galactic plane, in a pattern that repeated on both sides. The shape this implied was not a ball. It was more like a peanut, two lobes swelling symmetrically on either side of the galaxy's midplane, pinching inward toward the center and expanding again toward the edges in a form that is sometimes called the X shape, because when seen from the right angle outside the galaxy, the stellar density would trace something like a luminous X at the galaxy's heart. This shape is not a coincidence. It is the three-dimensional scar of an ancient dynamical event, specifically the thickening and folding of the central stellar bar under its own gravitational weight. The bar that runs through the inner galaxy, channeling gas and stars along its length, was not always the thickened X-shaped structure it is today. Long ago, it was flatter, more like a ruler than a knot. Over time, gravitational instabilities caused the bar to buckle, to fold upward on one side and downward on the other, symmetrically, repeatedly, like a thin strip of metal bending under compression. That buckling thickened the bar into the peanut shape, lifting stellar material above and below the plane, and cementing the three-dimensional structure that infrared surveys now map. The X shape is not decoration. It is evidence of an internal structural process that unfolded across billions of years, written in the positions of stars that have not moved significantly since. Among those stars, embedded throughout the ancient bulge, there are certain ones that behave differently from their neighbors. They do not simply shine at a fixed brightness, they breathe, they swell and contract, brightening and dimming, over a period of less than a single day. Each pulse is regular as a mechanical clock and governed by the same internal physics that has driven them since they formed more than 10 billion years ago. They are called RR-Lyrae stars, and they are among the oldest surviving stars the galaxy contains. An RR-Lyrae star is not large. It is a low-mass star, smaller and cooler than the Sun was when it was young, now in a late phase of its life, when the balance between gravity pressing inward and radiation pressing outward is not entirely stable. The outer layers of the star expand and contract in a slow rhythmic oscillation, expanding outward as the internal pressure builds, cooling slightly as they spread, then falling back inward as the pressure drops, then heating and expanding again. The period of this oscillation, for most RR-Lyrae stars, falls between a few hours and about a day. Because all RR-Lyrae stars of a given period burn at nearly the same intrinsic brightness, measuring the period gives the luminosity, and comparing the luminosity with the apparent brightness gives the distance. They are, in this way, both clocks and rulers, objects that carry their own measuring scale built into their light. The OLGL survey, a long-running program that monitored millions of stars toward the galactic center night after night, year after year, watching for brightness changes, cataloged tens of thousands of RR-Lyrae stars within the bulge. Their distribution across the sky and their distances revealed something important. They did not follow the same X-shaped peanut-like distribution that the red clump giants mapped. They were arranged more smoothly, more spherically, concentrated toward the center of the bulge, but not pinched into the same double-peaked form. This difference in shape between two populations of equally old stars living in the same general volume of space implies that they did not form in exactly the same way or at exactly the same time. The bulge carries within it at least two overlapping stellar populations with distinct structural signatures, one associated with the buckling bar, one apparently older and more smoothly distributed, both ancient, both present in the same region, layered on top of each other in a way that can only be unpicked by careful statistical mapping of hundreds of thousands of individual stars. There is something in that image worth sitting with. Two populations of ancient stars, older than the solar system by billions of years, occupying the same general space within the galaxy. Their histories different enough to leave different structural signatures, and yet both so old that from any ordinary human timescale, they are simply simultaneous. They formed in different episodes by different processes, and yet in the present moment, they share the same ancient, slowly brightening glow above the southern horizon on a clear summer night. The bulge does not look from the outside like a region containing multiple historical layers. It looks like a single, gentle brightness, but inside it, the record of at least two eras of the galaxy's earliest history is written in the positions of stars. The chemical record is equally layered. The stars in the bulge are not all the same in terms of their elemental composition, and the differences are not random. They follow a pattern. Stars at lower galactic latitudes, closer to the plane of the galaxy, nearer to the midplane of the disk, tend to be more metal-rich. They contain more of the heavy elements that form after hydrogen and helium, iron, magnesium, silicon, oxygen. Stars at higher latitudes, farther above or below the plane, tend to be more metal-poor, carrying less of these heavier elements, and in some cases approaching the elemental simplicity of the very early universe. This gradient is not a coincidence of sampling or measurement. It reflects something real about how the bulge formed and how it was chemically enriched. In the early galaxy, the first stars to form were massive and short-lived. They burned through their hydrogen fuel rapidly, fused heavier elements in their cores, and died in violent explosions called core collapse supernovae, scattering the products of their fusion outward into the surrounding gas. Each generation of massive stars thus enriched the gas from which the next generation formed, and the process happened quickly, in this context, meaning over perhaps 100 million to a few 100 million years, a fraction of the galaxy's total age, but still a span of time longer than any currently existing species has been alive. The inner parts of the proto-bulge, where gas densities were highest and star formation proceeded most rapidly, moved through this cycle of enrichment the fastest. Stars forming there early in the process were already forming from gas enriched by previous generations. Stars forming at larger distances from the center, where densities were lower, and the cycle of stellar recycling moved more slowly, began their lives from less enriched gas, and their chemical composition reflects that difference. Measuring these compositions requires spectroscopy, the technique of separating a star's light into its component wavelengths and reading the dark absorption lines that mark the presence of specific elements in the star's atmosphere. Large spectroscopic surveys, observing hundreds of thousands of bulge stars, have confirmed this gradient in detail and added important texture to it. Stars that are high in alpha elements, oxygen, magnesium, silicon, calcium, formed preferentially in the rapid nuclear burning of core collapse supernovae, point toward formation in that era of fast, intense enrichment, before the slower producing Type 1a supernovae had time to add large amounts of iron to the mix. The chemical compositions locked into these old stars are like isotopic labels, recording not just what elements were present when they formed, but something about the pace and scale of the stellar life and death that preceded them. There is a kind of patience required to read this record. The stars do not announce their ages or compositions. They simply shine, each one a stable and nearly unchanging point of ancient light, carrying inside the patterns of their spectral lines the entire history of the stellar generations that came before them. To extract that history requires measuring the brightness of millions of stars over many years, building instruments sensitive enough to spread starlight, thin enough to read its molecular fingerprints, and then calculating from vast data sets the statistical patterns that reveal the galaxy's history. The story of the bulge's chemical enrichment was assembled from exactly this kind of patient, cumulative, unhurried work, not from any single spectacular observation, but from the slow accumulation of detail over decades. The bulge also carries a record of something much smaller than stars. In the light curves of background bulge stars, stars simply shining steadily beyond the galactic center, there are occasional brief and precise brightenings that have nothing to do with the star itself. They are caused by gravity. When a massive object passes almost exactly between a background star and the Earth, the gravitational field of the passing object bends and focuses the background star's light, amplifying it for a few hours or a few days before the alignment dissolves and the star returns to its baseline brightness. The technique that detects this is called gravitational microlensing, and OAGL and subsequent collaborations have monitored the bulge for exactly this signal, watching tens of millions of stars night after night for the characteristic symmetric brightening that signals a chance alignment. Most lensing events are caused by passing stars. A single foreground star bends the background light into a smooth and symmetric brightening curve that rises and falls over the course of days to weeks. But occasionally, the brightening curve is interrupted, a brief, sharp additional peak superimposed on the smooth stellar lens curve, lasting only hours, too brief and too precisely timed to be a coincidence. These brief anomalies in the lensing signal are the signatures of planets. When the passing star has a planetary companion, and when the geometry of the alignment is just right, the planet's own gravitational field adds its own small lensing contribution to the event, a brief moment of additional magnification that, if detected and measured carefully, reveals the presence of the planet, its mass ratio relative to its star, and its orbital separation. The detection lasts only hours. It does not repeat. Once the alignment has passed, the information it carried passes with it, and the background star returns to its ordinary brightness without any lasting sign of what just happened. Dozens of planets orbiting bulge stars have been detected through this method. They orbit stars 20,000 light-years away in the most densely packed stellar region of the galaxy, surrounded by ancient stars formed billions of years before the Sun. Their existence confirms something important. Planet formation is not a process limited to the Sun's galactic neighborhood, or to stars of a particular age, or to the quiet, relatively sparse region of the Orion Arm where the solar system happens to reside. It is a process that operates throughout the galaxy, including at its oldest and most crowded center. Planets form wherever the conditions are right, and those conditions, it turns out, are available to the oldest stars in the bulge as readily as to any others. Those planets have been orbiting their stars for longer than the solar system has existed, in silence and in darkness, circling ancient suns that formed in the galaxy's very first chapter. The image is worth holding for a moment. A background bulge star, one among tens of millions, monitored by a survey telescope, brightens fractionally for a day, then fractionally more for a few hours in the middle of that brightening, then returns to its normal light. Within that brief additional brightening is encoded the entire existence of a planet, its mass, its distance from its star, its ancient and unwitnessed orbit. The planet itself is invisible. The star it orbits is barely detectable. What is seen is the bending of light around a gravitational field, a momentary lens effect in an event that will never repeat, and from that passing curve, a world is inferred. The stars of the ancient bulge do not change on human timescales. They will burn for billions of years more, most of them fading gradually as they age and cool, but not varying on any scale that a human life could observe. Their pulsations, where they exist, take less than a day. Their orbits around the galactic center take hundreds of millions of years. Between these two extremes, the rhythmic daily breath of the pulsating stars and the enormous, barely perceptible sweep of their orbital motion, there is almost nothing moving at a speed or on a scale that any individual human observation could track from start to finish. The galaxy's oldest population lives in a kind of deep stillness that is not the stillness of emptiness, but the stillness of processes too slow to resolve. The RR Lyrae stars, pulsating steadily throughout the ancient bulge, have been doing exactly what they are doing now for longer than the solar system has existed. They have been brightening and dimming over periods of less than a day, each oscillation following the next in an unbroken sequence for 10 billion years or more. No one was watching for most of that time. The pulsations continued regardless. Light was emitted, traveled outward, and was absorbed by the surrounding space, or scattered by dust, and nothing recorded it. The rhythm continued without witness, without measurement, without the faintest awareness of itself, as regular as anything in the galaxy, a heartbeat in the dark, in a place that existed before the Earth, before the sun, before the cloud of gas and dust that would one day collapse to form this part of the galaxy's disk, had even gathered itself into its final shape. That the glow above Sagittarius contains such things is not immediately obvious to any eye resting on it for the first time. It looks like light. It looks like a brightening of the night sky, a soft, diffuse patch where the stars are too numerous and too distant for the eye to separate them. But behind that unresolved luminosity, packed into a volume 10,000 light-years in every direction, is the deepest chapter of the Milky Way's history, the stars that formed first, the chemical record of the earliest stellar generations, the structural scars of a bar buckling under its own weight over billions of years, and the pulsing rhythms of ancient stars whose light has been crossing space since long before there was anyone here to receive it. The ancient light arriving from the bulge left its sources before the solar system existed. It has been crossing space for 20,000 years and more, and it arrives at the eye, or at the mirror of a telescope, or at the detector of an infrared camera, still carrying the information it was encoded with at the moment of emission. The spectrum of an old metal-poor RR Lyrae star in the outer bulge is not very different from the spectrum it would have shown when the light left it 20,000 years ago. Stars change slowly. Their compositions, once set at formation, alter only at the surface over the course of their lives, and only marginally. The ancient light is an accurate messenger. What it carries across 20,000 years is within small limits a true record of the star that sent it. What surrounds the bulge on all sides, beyond its diffuse outer edge, is the thinner and more structured disk of the galaxy, the broad, flat region of younger stars, gas clouds, spiral arms, and ongoing star formation that extends outward for tens of thousands of light years in every direction from this concentrated ancient core. The bulge does not end sharply, it fades. The stellar density decreases gradually with distance from the center, and at some point the population of stars transitions from predominantly old, metal-poor, randomly orbiting bulge stars to predominantly younger, more metal-rich disk stars, moving in the orderly, nearly circular orbits that characterize the galactic plane. There is no wall. There is no visible boundary. The two populations overlap in a transition zone where both are present, and distinguishing which star belongs to which structural component requires measuring individual compositions and orbital properties rather than simply looking at position. But the distinction is real. Disk stars and bulge stars are different kinds of objects with different histories, even though they currently occupy adjacent regions of space. The disk formed later from gas that had already been enriched by the bulge's first stellar generations, moving in the orderly rotation that the galaxy's overall angular momentum imposed on it. The bulge formed earlier, faster, more chaotically, from mergers and dense cloud collapses, in an era before that orderly rotation fully dominated. The bulge remembers that earlier time in the compositions of its stars, in their orbital eccentricities, in the peanut-shaped structural signature of their distribution, and in the pulsing light of its ancient variable stars. All of this compressed into the soft glow above the summer horizon. All of this, ancient and unwitnessed and patient, burning quietly at the center of everything, older than the world. The pulsating stars do not need to be seen to continue. They will brighten and dim through another full cycle in the time it takes to notice them, swelling slightly outward, cooling at the surface as the gas expands, then contracting again, heating, brightening for a few hours before the next slow inward fall. The cycle has no beginning that any observation has ever caught, and no end that any projection yet foresees. It continues in the deep interior of the ancient bulge, where the stars are old and steady, and the light they emit has been making its long crossing toward empty space since long before there was a planet here to receive it, rhythmic and slow and unperturbed, like something that has always been and quietly will be for a very long time still. A cloud of cold gas drifts in the dark between the stars, several thousand light years from the sun, deep within the arc of one of the galaxy's great spiral arms. It does not glow. It gives off no visible light. The cloud is made mostly of hydrogen, with traces of carbon monoxide and dust, and it has been drifting in this slow, irregular way for millions of years, barely changing, barely moving by any measure a single human lifetime could detect. But something is beginning to happen to it. The arm it drifts within is not a fixed wall or a rigid structure. It is more like a region of slightly deeper gravity, a slow wave moving through the disk of the galaxy, a place where the invisible floor of space tilts gently inward, and gas drawn toward that deepening begins to pile against itself the way shallow water thickens against a sandbar. The cloud is falling, in the gentlest sense of the word, into the arm's interior density, and as it falls, something long suspended in it begins at last to change. This is how spiral arms do their work, not with force or sudden impact, but with patience. The arm moves through the galaxy's disk at a speed different from the stars and gas clouds that inhabit the disk, slightly slower, slightly offset, so that over tens of millions of years, one cloud after another drifts into the arm's influence, is compressed, and passes through. Clouds enter from one side, clusters of newly formed stars emerge from the other, carried along by the disk's rotation, drifting free of the arm that made them. The arm itself stays behind, filling again with the next wave of approaching gas, the pattern sustaining itself across timescales that have no human analog. What looks from outside like a frozen structure is in practice a long, slow river of transformation. The spiral arms of the Milky Way curl outward from the ends of the galaxy's central bar in curves called logarithmic spirals, a shape found in other things as well, in the chambers of a nautilus shell, and in the arrangement of seeds in a sunflower head, though the connection is one of mathematics and not of any shared origin. There are four primary arms. The Norma arm winds close to the galactic center. The Scutum Centaurus arm and the Perseus arm are the two most massive, thick with gas and new stars, tracing the longest continuous arcs. The Sagittarius arm runs between them, somewhat thinner, its bright young clusters visible on dark summer nights as the faint luminous band that thickens toward the constellation Sagittarius. These arms do not rotate as solid objects. Each star within the disk follows its own orbit, its own private ellipse around the galactic center, slightly different from every other star's orbit. The arm pattern moves through this sea of individual orbits, like a wave moves through open water. The water itself goes nowhere in particular, but the wave moves steadily forward, and at any given moment, the water in the wave is higher and closer together than the water on either side. The mathematical description of this came together in the 1960s, when two researchers named Chia-Chow Lin and Frank Hsu worked out the equations for what they called a density wave. The idea was that the spiral arms were not material objects, but quasi-stationary waves, regions of slightly elevated density rotating through the disk at a speed different from the stars themselves. Gas clouds caught in the wave's gravitational reach would be compressed at the arm's leading edge, and this compression would be enough to push a cloud past the threshold where its own gravity could take over. Stars would begin to form within it. By the time the arm's crest had passed, the young stars would be left behind, shining brightly, marking the arm's location like lights strung along a wave's highest reach. The arm itself would be replenished from behind by the next generation of approaching clouds. The picture that came from this work had an elegant internal logic. The arms sustain themselves not by holding on to material, but by triggering the same transformation repeatedly, in cloud after cloud, over billions of years. The Scutum Centaurus arm, the largest and most prominent of the four, is traced in radio surveys by a nearly continuous bright ridge of emission from cold carbon monoxide gas. Radio wavelengths pass through dust that blocks all optical light, so the arm's molecular skeleton becomes visible to instruments that measure photons, too long to see. In the radio maps, the arm appears as a luminous arc curving across the inner galaxy, glowing not with heat, but with the quiet microwave emission of molecules vibrating at their own particular frequencies. Along its length, one molecular cloud complex follows another, each one a reservoir of hundreds of thousands or millions of solar masses of cold gas waiting in the dark. These are the raw material for the arm's next generation of stars, already gathered and cooling, already slightly denser than the space between the arms. They are not yet stars, they are still clouds. But the arm has begun its slow work on them, and in a few million years, a very brief time by galactic standards, some fraction of their mass will have collapsed into new suns. Between the arms, the gas thins and quiets. The molecular cloud complexes that dominate the arm's interior give way to more scattered, lower density regions. Star formation does not stop entirely in the inter-arm space, but it slows. The bright blue-white clusters of young stars that mark the arms like beads on a curved thread are absent here, or sparse. The inter-arm regions are older-feeling places in the sense that the light there is mostly the warm orange and yellow of stars that formed long ago, whose short-lived blue siblings have already burned through their fuel and are gone. The arm is where the present happens. The space between is where the past lingers. One of the best-known star-forming regions in the sky sits in the Orion arm, the partial arm, or spur, in which the sun itself resides, a structure roughly 10,000 light-years long that bridges the gap between the Sagittarius arm and the Perseus arm. The Orion Nebula hangs in the sword of that constellation, visible to the naked eye on a clear winter night, as a faint smudge in a region of sky crowded with young blue stars. Through even a modest telescope, it resolves into a luminous green-gray cloud, lit from within, its glowing interior crisscrossed by dark filaments and bright knots of denser gas. The light it gives off is not reflected starlight. It is the gas itself responding to radiation, the hydrogen atoms absorbing ultraviolet photons from a cluster of young hot stars at the nebula's center, then releasing that energy again at specific visible wavelengths, a red-pink glow in long-exposure photographs, and a pale greenish shimmer to the dark-adapted eye. At the nebula's heart, 4 bright stars cluster together in a tight group called the trapezium, only a few 100,000 years old, newborns by cosmic measure, barely settled into their hydrogen-burning lives. Their radiation is what powers the surrounding cloud's glow. The Orion Nebula is not a vast structure by galactic standards. It spans roughly 24 light-years across its brightest region, a small bright patch within a much larger, dark molecular cloud that lies just behind it, the Orion Molecular Cloud, which stretches for hundreds of light-years and harbors the formation of thousands of stars at various stages of development. The nebula is just the illuminated face of that cloud, the part that the trapezium's radiation has ionized and made visible. What lies behind is dark and cold and full of beginnings not yet lit. This is what an HI region is, a cloud of ionized hydrogen surrounding newly formed massive stars, glowing in response to the radiation those stars produce, marking the arm's location like a bright spot in a long and mostly invisible thread. There are many of them: the Lagoon Nebula, and the Eagle Nebula, and the Carina Nebula, and dozens more, each one a node in a spiral arm's luminous surface, each one containing somewhere in its interior the quiet dark machinery of new star formations still underway. Radio astronomers have used the characteristic emission of neutral hydrogen, a specific microwave frequency produced when the electron in a hydrogen atom flips its spin state, to map the arms across the full width of the disk, even through the thick dust lanes that make optical surveys impossible in many directions. At 21 centimeters wavelength, the galaxy's hydrogen becomes transparent to observation, and the radio maps built from these observations over many decades reveal the full extent of the ARM system. Arcs of emission stretching for tens of thousands of light-years, curving outward from the bar, their distances inferred from the Doppler shift of the signal, as each cloud's orbital speed carries it toward or away from the measuring instrument. The maps are not perfect. Looking outward along an arm creates ambiguities where 2 clouds at different distances can appear in the same direction at similar speeds, but the broad picture has held for decades, confirmed and refined by more recent techniques, including the direct measurement of stellar distances through radio parallax, tiny shifts in position measured against background sources as the Earth orbits the Sun, a surveying technique applied at interstellar range. From those radio parallax surveys, part of a program called the Bar Spiral Structure Legacy Survey, researchers have measured the precise distances and positions of star-forming regions scattered throughout the disk, pinpointing their locations in the galactic plane and confirming the general geometry of the ARM system. The work is slow. Each maser source, a small intense radio-emitting region associated with a forming massive star, must be measured repeatedly across multiple years to detect the tiny positional wobble that gives its distance. But the distances accumulate, and with them, a more detailed three-dimensional picture of where the arms actually lie and how tightly they are wound. The picture that has emerged places the Sun roughly 26,000 light years from the galactic center, in its own modest spur, between two more massive arms, drifting through a region of intermediate gas density at a speed of roughly 220 kilometers per second around the center. At that speed, one full orbit of the galaxy takes the Sun somewhere between 225 and 250 million years. That span of time has a name sometimes used informally, a cosmic year or a galactic year. The solar system has completed between 17 and 20 such orbits in the time since it formed. A single one of them contains enough time for the entire recorded history of human civilization to repeat itself more than 2 million times. One orbit covers the lifespan of entire species, the rise and fall of mountain ranges, the slow drift of continents from one arrangement to another. Within a single cosmic year, the Sun has drifted past or through the edges of spiral arms, passed through regions of elevated star formation, and traced a slow spiral path through the galactic disk as various gravitational influences have nudged its orbit by tiny amounts. The Sun is not fixed in the arm, it drifts through, as everything does. The interarm region the Sun currently occupies has a particular texture. The gas here is thinner than in the major arms. The density of star-forming molecular clouds is lower. There are no massive young stellar clusters within a few hundred light years, no bright HI regions close enough to see as extended glowing patches with the naked eye, only the Orion Nebula at just under 1,400 light years, and a few others within a few thousand light years, marking the edge of the Orion spur. The sky, as a result, is quieter than it would be from within a major arm. Closer to the center of the Scutum Centaurus arm, the sky would fill with young open clusters and glowing nebulae. Here the light is more subdued, an older, warmer glow, with only a few bright young objects visible as exceptions. This is not a disadvantage. It is simply a position, one stop along a long arc, and in some sense the quietness of the region has made it a stable place for the last few billion years. The spiral arms themselves are not permanent. The pattern can sustain itself for long periods, but the details change. Arms can branch. They can fade in some sectors and brighten in others as the supply of incoming molecular gas varies. They can be perturbed by close passages of other galaxies, their clean logarithmic curves pulled into irregular shapes by tidal forces. The Milky Way's arm pattern, as seen in radio and infrared maps, is not perfectly symmetric. The Scutum Centaurus arm and the Perseus arm are more prominent than the others. There are regions of the arms where the star formation is especially vigorous, where a large complex of molecular clouds has been compressed and multiple clusters are forming simultaneously, and regions where the arm seems quieter, its gas thinner, or already consumed. The arms are alive in the sense that they change, that they respond to conditions, that the same basic process repeats endlessly along their length without repeating identically anywhere. The gas that enters an arm and is compressed into star-forming clouds follows a path that can be traced in broad strokes, even if the details of any individual cloud's history remain uncertain. A cloud drifts through the interarm region over tens of millions of years, gradually cooling, accumulating mass through slow collisions with smaller clouds, maintaining a rough internal equilibrium between the warming effect of cosmic radiation permeating the disk and the cooling effect of molecular emission from its own gas. As it approaches the arm's leading edge, the density around it begins to rise. The cloud finds itself in a slightly deeper gravitational well. It begins to compress, not rapidly, not violently, but slowly and at large scales, the outer layers of the cloud pulling inward, the interior growing denser. At some point within this compression, the cloud's own self-gravity begins to win against the turbulence and magnetic pressure that have kept it inflated. Individual clumps within it cross the threshold and begin their own collapse. Stars begin to form. The most massive stars that form within such a cloud, those 10, 20, or 50 times the mass of the Sun, do not last long. They burn through their fuel in millions of years, and before they die, they pour out so much ultraviolet radiation that they ionize the surrounding gas, creating the glowing HI regions that trace the arm. They drive stellar winds that push the cloud's remaining gas outward, compressing it further, perhaps triggering the formation of a second generation of stars at the cloud's edges. When they finally exhaust their fuel, they explode as supernovae, blasting energy into the surrounding medium, enriching it with heavy elements forged in their cores, carving cavities in the molecular cloud complex that may persist for millions of years. The arm continues. The next cloud approaches. The pattern repeats. The Eagle Nebula, about 7,000 light-years away in the Sagittarius Arm, contains one of the most recognizable structures in astronomy: 3 tall columns of dark molecular gas rising from a denser base, their surfaces being eroded away by the ultraviolet radiation of a nearby cluster of young massive stars. The columns, each several light-years tall, are made of the same cold hydrogen and dust as the molecular cloud from which they formed, but they are denser than their surroundings, and so they resist the erosion longer. The glowing surfaces are the boundary between the column's cold interior and the hot ionized gas that surrounds them, where the radiation field meets the cloud material and ionizes it, producing a faint, persistent glow. Inside the columns, hidden from optical view, new protostars are forming in the quiet dark, sheltered for a time by the very walls that are being slowly consumed around them. The erosion will continue. The columns will be gone in a few million years, their material dispersed into the surrounding nebula, but by then, some of what formed within them will have become young stars, drifting free of the cloud in which they began. The HI regions and molecular clouds that mark the arms are not uniformly distributed along their length. They clump and cluster into hierarchical structures, giant molecular associations spanning hundreds of light years, within which smaller cloud complexes nest, within which individual cloud cores collapse to form stellar clusters. The largest associations can contain tens of millions of solar masses of gas spread across a region large enough to hold many separate star-forming events simultaneously, each one proceeding at its own pace and in its own local environment. The arm traces through all of them, linking them into a continuous structure by proximity and by the common pattern of compression and formation that drives them all. Seen in a radio map, this hierarchical structure gives the arm a textured, granular appearance, not a smooth ridge, but an irregular beaded chain, brighter in some places than others, with gaps and clumps and dense knots where the gas has collected most heavily. The arms also carry the history of the disk's chemical evolution written in the stars that have formed within them. Stars that formed early in the galaxy's history, in a time when the disk had fewer heavy elements, carry that chemical poverty with them wherever they drift. Stars that formed more recently, after billions of years of supernovae had enriched the disk's gas, carry more of the heavier elements, because the arms have been continuously forming stars throughout the disk's history. Their stellar populations contain this full chemical record layered within them, the older stars drifting outward toward the disk's edge or scattered above and below the plane, the young massive stars still close to the arm, where they were born, the medium-age stars somewhere in between, each population chemically stamped with the era of its formation. The arms are not just structures in space, they are also structures in time. Each a molecular cloud that has just been compressed at the leading edge of the Scutum Centaurus arm may contain within it, right now, the earliest stages of what will eventually become a planetary system. The collapse of the cloud's densest core will produce a protostar surrounded by a flattened rotating disk of gas and dust, a disk whose composition reflects everything the cloud accumulated during its long inter-arm drift, including the heavier elements returned to the gas by earlier generations of supernovae in the arm itself. The disk will persist for millions of years. Within it, dust grains will collide and stick together, building larger and larger bodies through a slow accumulation that operates at scales far below what any present survey could detect. At these early stages, the future planetary system is invisible in every observational sense. It is just part of the cloud, a slightly denser region within a collapsing core, its eventual structure completely unwritten. The gas between the arms does not sit still while the arms do their work. The disk is threaded by magnetic field lines that run roughly parallel to the arm structure, and these fields influence how gas moves, how it collapses, and how efficiently star formation proceeds in different locations. In the inter-arm regions, the magnetic field tends to be relatively ordered, following the galactic structure in long, smooth lines. Within and near the arms, turbulence and the energy input from massive stars and supernovae tangle the field, creating a more disordered and complex magnetic environment. This tangling matters for how molecular clouds form and how dense they become before collapsing. A cloud threaded by a strong, ordered magnetic field can resist collapse better than one whose field has been disrupted. The arms, paradoxically, disrupt the field through the very star formation they drive, creating conditions that can then either facilitate or impede the next wave of collapse. There is a rhythm to all of this, though it operates on time scales that make the word rhythm feel inadequate. A cloud drifts through the inner arm space for tens of millions of years. It passes through the arm in a few million years. The stars it produces live for a range of lifetimes, the most massive for only a few million years, the most modest for far longer than the current age of the universe. The arm pattern itself has probably persisted for several billion years in roughly its current form, long enough for the Sun to have completed many orbits and passed through arm regions many times. Through all of this, the disk of the galaxy maintains its basic shape, flat, rotating, slowly enriching itself in heavy elements, generation by generation, the spiral arms marking the places where the transformation concentrates. The Orion arm, the modest spur in which the Sun presently drifts, gives little visual hint from the inside of the larger structure it is part of. On a clear dark night, what is visible is the Milky Way, a band of diffuse light running around the full sky, brightest towards Sagittarius, where the galactic center lies behind it, thinner and paler toward the anti-central direction. The band is the disk seen edge-on from inside, the combined glow of hundreds of billions of stars, too distant and too numerous to resolve individually. Within that band, two kinds of texture are visible. There is the glow itself, warm and diffuse, and uniform at the limit of naked eye resolution, and there are the dark lanes running through it, irregular threads and patches of darkness, where intervening dust clouds absorb the background light, cutting the glow into separate islands and rivers of brightness. The dust lanes are not voids, they are presences. They are the foreground molecular clouds of the Orion arm and the inner edge of the Sagittarius arm, the same cold dark gas, that will eventually be compressed and lit and carried through the long, slow transformation the arm performs on everything that enters it. The Sun sits in its current position at roughly the midpoint of the Orion spur's length, drifting in the general direction of the constellation Cygnus as it follows its galactic orbit. It has been in approximately this region of the disk for the entirety of the solar system's existence. Roughly 1 cosmic year has elapsed since the solar system formed from a collapsing cloud that was itself part of a spiral arm, active at that time. The chemical composition of that original cloud and of the star and planets that formed from it reflects the enrichment history of the disk at the Sun's galactocentric radius 4.5 billion years ago. The carbon in organic molecules, the oxygen in the atmosphere, the iron in planetary cores, all of it arrived in that original cloud via the supernovae and stellar winds of earlier generations of arm-born stars, cycling through the interstellar medium across billions of years before finding its way into the cloud that became the solar system. The arm that made the Sun no longer exists in the same form. The arm pattern has shifted, but the material that passed through it endures, carrying forward the chemical legacy of everything the arm processed before it. In the dark, in a direction roughly toward the constellation Scutum, the inner edge of the Scutum Centaurus arm begins. It lies not far beyond the end of the galaxy's central bar, where the bar's gravitational influence funnels gas outward into the arm's root. Radio maps show it beginning there as a dense bright ridge and curving slowly away, growing and brightening as it picks up the gas accumulated from the bar's interior. Along its length, one star-forming region follows another. The W51 complex, among the most luminous HI regions in the galaxy, glows there in the radio. The W49A complex, another giant star-forming site, marks another bright node along the same arm. These are places where the arm's compression has collected many millions of solar masses of gas into a single enormous cloud complex, and the star formation within them proceeds at a rate that far exceeds anything in the Sun's immediate neighborhood. They are bright enough to be detected in radio and infrared surveys from across the entire galaxy, their emission reaching instruments on Earth, even though the dust between them and us absorbs nearly all their optical light. The Perseus arm, curving outward on the far side of the Sun from the galactic center, is the outermost of the four main arms and one of the most clearly delineated. It runs along a track several thousand light-years beyond the Orion spur, its location confirmed by the precise radio parallax measurements of maser sources embedded in its star-forming regions. The double cluster in Persea, two open clusters of young blue stars visible to the naked eye as a faint double haze near the border of Perseus and Cassiopeia, sits near the inner edge of this arm, their combined light reaching the eye after traveling more than 7,000 light-years. They are young clusters, only a few million years old, still bright with the blue-white light of their most massive members. In a few tens of millions of years, those massive members will be gone, and the clusters will fade and redden and slowly disperse, their stars joining the general disk population as the arm moves on and leaves them behind. The arms do not end abruptly. They thin and become less distinct as they approach the outer disk, where the gas density drops and the conditions for star formation become less favorable. The outermost regions of the disk hold some star formation. HI regions and young clusters have been detected at galactocentric distances far beyond the Sun's orbit, but the spiral structure becomes harder to trace and the arm pattern becomes less organized. The outer disk is a quieter, sparser place, where the arm-driven transformation that dominates the inner galaxy occurs only sporadically in widely separated pockets of gas dense enough to begin the long process of collapse, and widely separated pockets of gas dense enough to begin the long process of collapse, and the full arc of a spiral arm from its root at the bar's end to its fading in the outer disk spans many tens of thousands of light years, the time a gas cloud spends within an arm's influence, from compression to the birth of new stars to the dispersal of those stars into the disk, may span 10 to 20 million years. The time between one arm passage and the next for a cloud at the sun's galactocentric radius is perhaps 1 to 200 million years. Over the lifetime of the disk, each parcel of gas has passed through the arm compression many times, forming stars, being dispersed, recondensing in the inter-arm space, drifting toward the next arm. The disk is not a static structure with spiral arms painted on it. It is a slowly churning engine in which the arms are the active zones, the places where the disk's ordinary, distributed material is repeatedly gathered and concentrated and transformed. The arm that the sun moves through now, the Orion spur, the partial arm, the bridge between the Sagittarius and Perseus structures, is quieter than the main arms. It has star-forming regions. It has young clusters and HI regions, but it does not have the continuous dense molecular ridge of the Scutum Centaurus arm, or the long unbroken bright chain of star formation in the Perseus arm. The Orion spur is a secondary structure, a gravitational eddy in the disk's flow, a feature that may persist for a few 100 million years, or may gradually fade as the larger arm pattern shifts. The sun will drift out of it in time, as it has drifted into regions of different character before. The disk continues, and the arm continues, and the gas continues moving through both of them, gathering and dispersing and gathering again. From very far outside the galaxy, at a distance of a few 100,000 light years, the same distance at which the Magellanic Clouds orbit the Milky Way, the full spiral structure would become visible at once, the way the full pattern of a whirlpool becomes visible from the air above a river. The bar would run through the center, its two ends feeding the roots of the two primary arms. The arms would curve outward from those roots in their logarithmic spirals, each one a slow bright arc traced by the combined light of their youngest and hottest stars. Between the arms, the older, cooler stars of the disk would glow with a softer light, less blue, less dramatic, but present everywhere, filling the space between the arms' bright edges with the warm accumulated output of billions of years of star formation. The whole structure would be turning, the bar rotating, the arms maintaining their pattern against the flow of individual stars and gas clouds, orbiting at their own speeds, the outer disk turning more slowly than the inner, the entire disk spinning in the same direction as the arm's wind. The winding is slow, the rotation is steady, the transformation that the arms perform has been running more or less continuously for most of the galaxy's history. The sun drifts in the Orion spur at 220 kilometers per second, following the broad curve of its galactic orbit, tracing a path that over the course of 1 billion years closes back on itself in a slow ellipse. It does not feel this motion. There is no wind of stars, no sense of speed, no visible shift in the star patterns over any timescale a human life could encompass. The stars nearby drift imperceptibly relative to one another across decades, and the large-scale structure of the galaxy, the arms, the bar, the central bulge, appears fixed and still in every human observation. The motion is real, and the galaxy is real, and the arms are real structures moving through a disk of real stars and real gas. But the scale at which they are real is so far beyond the scale at which anything is felt that the galaxy exists for any living thing within it as a kind of permanent background, ancient, turning, ongoing. The cold gas in the Scutum Centaurus arm goes on accumulating, cloud by cloud, in its dense molecular ridge. The young stars in the Eagle Nebula go on eroding the dark columns that shelter the protostars within them. The double cluster in Perseus goes on drifting, slowly dispersing, its brightest members burning toward their ends. The Orion Nebula goes on glowing, lit from within by its four young trapezium stars, their combined radiation slowly eating back the dark cloud behind them. And the sun goes on moving through the quiet inner arm space of the Orion Spur, carrying its 8 planets and the long, thin disk of the asteroid belt and the distant scattered shells of the outer cometary reservoirs, all of it together drifting at 220 kilometers per second in the slow, endless curve of its galactic orbit, neither rushing toward the next arm nor retreating from the last, simply passing through the disk the way all things pass through it, drawn by the same gravity, carried by the same rotation, part of the same slow turning that has been turning since long before any of the stars now shining were born. In the photograph of an edge-on galaxy, the disk is a single bright smear drawn across the dark. The center burns, the arms spread outward, and bisecting that bright band from one end to the other, running through its equator like a drawn line, is a darkness so consistent and so thin that it looks as though someone pressed a thread of shadow into the light. That thread is not empty. It is not an absence. It is dust, silicate and carbon grains drifting in clouds between the stars. And in a galaxy seen edge-on like that, the whole dusty layer of the disk compresses into something that, against the width and brightness of all those stars, looks barely thicker than a seam. The Milky Way is that galaxy. Its disk stretches roughly 100,000 light-years across, and within that enormous breadth, the dust and gas are gathered into a sheet, only a few hundred light-years deep, so flat relative to its width that the comparison to paper is not an exaggeration, but a measured fact. The dust is not distributed smoothly. Nothing in the disk is smooth. On a clear night, far from city light, looking toward the band of the Milky Way overhead, the eye is drawn not only to the bright lanes, but to the dark ones, rifts and wedges and branching channels of shadow cutting through the glow. These dark regions are close. Some are only a few hundred light-years away, near neighbors on the scale of the galaxy, and they look dark not because they contain nothing, but because they contain so much. A cloud of interstellar dust, dense enough, absorbs the light of every star behind it. Billions of suns, ancient and burning, lie on the far side of these clouds, and none of their light arrives. The cloud intercepts it. The dust scatters and absorbs the shorter, bluer wavelengths first, so whatever light does leak through is reddened, warmed in color the way the sun reddens near the horizon when its light passes through more of the atmosphere. But in the densest directions, near the equator of the galaxy where the dust layer runs thickest, not even that reddened light gets through. Dozens of magnitudes of extinction can accumulate along a single line of sight through the plane, enough to stop not just a little light, but virtually all of it. The galactic center, burning at its core, is completely invisible to the naked eye and to any ordinary optical telescope. The dust between here and there is a wall. The dust grains themselves are small, not invisible small in the vague sense, but measurably, specifically small, comparable in size to the wavelengths of visible light, which is why they scatter and absorb that light so effectively. They form in the cooling outer layers of dying stars, where carbon and silicon condense out of the outflowing gas the way frost condenses on a cold surface, and they drift outward into the surrounding space, accumulating over millions of years into the diffuse clouds that gather between the stars. Inside those clouds, the grains become coated with ices, water and ammonia, and carbon monoxide frozen onto their surfaces in the cold, shielded interior, so that the grain at the heart of a dense cloud might be a hard mineral core, wrapped in a thin mantle of frozen molecules, drifting in a darkness so cold that the ice never melts, never evaporates, enduring for millions of years without interruption. When a survey uses infrared light or the longer wavelengths of radio, these clouds become visible again. The dust that blocks ordinary light is nearly transparent at those wavelengths, and what was a wall becomes a window. Infrared telescopes and radio dishes have mapped the full three-dimensional architecture of the dusty interstellar medium, its filaments, its dense clumps, its long hollowed corridors carved by supernova blast waves, and the picture is not a smooth sheet, but a layered, tangled, constantly stirred structure, threaded through with structure at every scale. The three-dimensional dust maps now assembled from the photometry of hundreds of millions of stars show the disk's dust layer as anything but flat in its details. There are fingers of dust reaching upward from the midplane. There are cavities blown clear by ancient explosions where the density drops sharply and stars are visible again at great distances. There are filaments that run for hundreds of light years without breaking, tracing the edges of molecular cloud complexes the way the banks of a river trace the water that carved them. Each filament is a potential cradle, the densest of them, drawn together by their own gravity and by the compression of shocks passing through, can cool and thicken until the weight of the gas exceeds the pressure that holds it up, and then it collapses, first in the densest pockets, then deeper, drawing the surrounding material inward in a slow implosion that over hundreds of thousands of years builds a star. The dust is not simply blocking light, the dust is building stars, and those stars are building the next generation of dust. The disk of the Milky Way is not made of dust alone. It is made of stars in their millions of billions, arranged in a structure with a distinct layering that took time and chemistry to produce. The thinner, more concentrated layer, close to the midplane, holds the young population, stars only a few billion years old at most, sometimes only millions, born in the molecular clouds and drifting only slowly away from the plane under the disk's own gravity. Their orbits are nearly circular, nearly flat, well ordered, in the manner of things that have not yet been disturbed too many times. Mixed in with them are the gas clouds, and the young star-forming regions, and the great ionized clouds lit brilliantly by the hottest newly born stars. This is the thin disk, and it is the most actively generative part of the galaxy, the layer where star formation is still happening, where the chemistry of the interstellar medium is still being refreshed by each generation of stellar lives and deaths. Above and below that thin, active layer, reaching out to a scale height roughly 10 times larger, is the thick disk. It is older. Its stars formed in the galaxy's first few billion years before the disk had fully settled into its current thin configuration, and they carry the chemical memory of that early time in their spectra. The stars of the thick disk have lower abundances of iron relative to the Sun, but their alpha elements, oxygen, magnesium, silicon, calcium, are relatively higher in proportion. This imbalance is a chemical clock. The alpha elements are made in the cores of massive stars and released promptly when those stars explode as core collapse supernovae, events that take only a few million years From birth to death, iron is produced more slowly, mostly in a different kind of supernova that requires a longer lived, lower mass star to reach its end. When the first generations of massive stars exploded quickly after the galaxy formed, they flooded the interstellar medium with alpha elements before the slower iron producing events had time to contribute. Stars formed in that early enriched gas carry a high alpha to iron ratio, a signature of rapid, intense chemical evolution driven by a flood of massive stellar deaths in a short time. The thick disk stars carry exactly this signature. They formed fast, in a galaxy that was burning through its first generation of massive stars, and they have been drifting in their slightly tilted, slightly eccentric orbits ever since, slowly mixing above and below the plane in a layer that is older and quieter than the thin disk below them, but still present, still orbiting, still carrying the record of what those first few billion years were like. Between the stars, in all directions, the space is not empty. It never is. The interstellar medium fills every part of the disk, occupying the space between the stars. The way water occupies the space between grains of sand in a wet beach, except that the proportions are impossibly more extreme. The stars are far more widely separated, the medium between them far more tenuous, and yet somehow the material accumulates over the vast distances into something with real mass, real chemistry, real structure. The interstellar medium exists not in a single state, but in several, all present at once within the same volume of the disk, coexisting, the way hot and cold air coexist in a room, in patches, in eddies, always exchanging energy at their boundaries, but never fully blending into a single uniform thing. The coldest parts are the molecular clouds, deep inside, shielded from ultraviolet radiation by the surrounding dust. The gas cools to temperatures only a few degrees above absolute zero, cold enough that hydrogen binds into molecular pairs, that carbon monoxide forms and persists, that complex organic molecules assemble slowly in the gas phase and on the surfaces of dust grains. The darkness inside a molecular cloud is total. No starlight penetrates to the deepest cores. The only light is the slow, faint glow of molecules releasing energy as they transition between rotational states, at wavelengths so long they pass through walls of matter that stop anything shorter. In these cold cores, the gas is so dense and so shielded that it has already begun to separate from the general flow of the disk, to turn inward on itself, to accumulate toward the conditions that will eventually produce a star. Surrounding those cold cores, warming outward through the cloud's outer layers and into the general interstellar medium, the gas passes through a range of temperatures and ionization states. Neutral hydrogen pervades the disk in a warm phase, filling the spaces between the dense clouds at temperatures of several thousand Kelvin, moving in slow drifts and turbulent eddies, detectable across the entire galaxy at a radio wavelength that passes through dust without loss. The 21-centimeter line, a signature of neutral hydrogen that has allowed radio astronomers to map the full breadth of the galactic disk, even through the most opaque directions. This warm neutral medium is the fabric of the disk's gaseous interior, the ambient sea in which the colder molecular clouds are embedded like islands, and into which the hotter gas ejected by supernovae is always bleeding heat. That hotter gas is the third great phase of the interstellar medium. A massive star ends its life explosively, the outer layers expelled in an expanding shell that compresses and heats the surrounding interstellar gas to temperatures of millions of Kelvin, far hotter than the surface of any ordinary star. Heated not by nuclear burning, but by the kinetic energy of the explosion, transmitted as a shock. This shock wave expands outward at speeds of thousands of kilometers per second in its first moments, sweeping up the surrounding medium, building a thin, dense shell at its front edge, leaving behind a hot, rarefied bubble of gas that glows not in visible light, but in the soft X-ray part of the spectrum. The hot bubble expands and cools over millions of years. The shell at its front edge thins and slows. Eventually, the pressure difference between the hot interior and the surrounding warm medium falls too low to drive further expansion, and the bubble stalls, mixes, diffuses back into the ambient gas. But while it lasts, it fills a significant fraction of the disk's volume with this million Kelvin gas, a gas so tenuous that it has almost no mass but occupies vast cavities carved into the structure of the disk. The disk, seen in cross-section through the right kind of telescope, is Swiss cheese architecture, cold dense clouds embedded in warm neutral gas, carved through with hot empty cavities, and all of it threaded by magnetic fields that resist the compression of the gas while conducting and guiding the energetic particles born in those same ancient explosions. Christopher McKee and Joseph Ostraker, two American astrophysicists, set down the foundational framework for this picture in 1977, proposing that the interstellar medium exists in three phases held together by the pressure equilibrium between them. The framework has been refined many times since. There are more phases recognized now. The transitions between them are more complex than a simple equilibrium picture describes, and the role of turbulence in driving the medium's structure has become a central concern of the field. But the core picture holds. The disk is a thermodynamic patchwork. Hot, warm, and cold coexist because each phase is continuously fed and continuously drained by the explosions of stars that heat the hot medium, by the cooling of that gas back into the warm medium, by the slow condensation of the warm medium into cold clouds, and by the collapse of those clouds into new stars, whose eventual deaths refuel the whole cycle again. Moving through all of this, invisible and persistent, are the cosmic rays. They are not light. They are not gas. They are individual particles, mostly protons, the bare nuclei of hydrogen atoms, with a small fraction of heavier nuclei, moving at velocities close to the speed of light, threading through the magnetic field of the disk in long spiraling paths that take them everywhere and nowhere particular. A supernova remnant accelerates them. The mechanism is subtle. The particle crosses the shock front of the expanding remnant, gains a small amount of energy from the compression there, crosses back, gains a little more, crosses again. Each crossing adds a fraction of energy. Over many crossings, over thousands of years, as the remnant expands and the shock slowly weakens, the particle accumulates enough energy to break free, spinning out into the disk in a trajectory determined by the magnetic field that permeates the interstellar medium. The field is tangled. It bends and loops and folds, threading through the clouds and the cavities in the warm neutral medium in a structure that is organized on large scales and turbulent on small ones, and the cosmic ray particle follows it, deflected at each bend, slowly diffusing through the disk in a path that zigzags across thousands of light years over millions of years before the particle finally escapes into the space above and below the plane. Near the sun, the energy carried by cosmic rays in each unit of volume is comparable to the energy carried by the interstellar magnetic field, and comparable also to the thermal energy of the warm interstellar gas. This near equality of energy densities among three very different components of the disk, charged particles, magnetic fields, and thermal gas, is not a coincidence. It is the signature of a system that has found a kind of rough equilibrium where each component feeds back on the others and none dominates for long. The cosmic rays exert pressure. They push against the magnetic field. They drive a slow wind of material upward out of the disk into the halo above and below. They ionize the cold gas at the edges of molecular clouds, changing the chemistry that determines whether and how quickly those clouds form stars. They are not passengers in the disk. They are participants, shaping it, pressing on it, leaking out of it over the course of 15 to 20 million years, and then being replenished by the next round of supernova explosions in the spiral arms. The thin disk, the thick disk, the interstellar medium in its phases, the magnetic field, the cosmic ray sea, all of this is organized within a plane. A flat plane, apparently, when seen in the inner and middle parts of the galaxy. But flatness is a local approximation, and it breaks down at the edges. Beyond a certain distance from the center, somewhere in the range of 25 to 30,000 light years, the outer disk begins to deviate from the plane defined by the inner disk. It does not stay flat, it bends. The bending is gradual. At 30,000 light years from the center, the deflection is small enough to pass unnoticed without careful measurement. At 40,000 light years, it becomes significant. At 60,000 light years and beyond, the disk has bent by several thousand light years out of the plane and not in the same direction on both sides. On one side of the galaxy, the outer disk curves upward. On the other, it curves downward. The shape is not a simple dish or bowl. It is an S-curve, a slow warp that twists the disk's outer edge into a configuration that, seen from above the pole, looks like an asymmetric pinwheel. This S-shaped warp was first noticed in the 1950s through observations of neutral hydrogen at radio wavelengths, when astronomers tracing the 21-centimeter emission across the sky found that in the outermost parts of the galaxy, the hydrogen was displaced from the plane they expected. More recent surveys, using Cepheid variable stars as precise distance markers, using the infrared light of old red giant stars, using the three-dimensional mapping made possible by the Gaia satellite, have confirmed the warp in multiple independent tracers and shown it to be a real three-dimensional distortion of the disk's structure, present not just in the gas, but in the stellar population as well. What caused it is not settled. The Magellanic Clouds, the two small satellite galaxies visible from the southern hemisphere as bright patches against the night sky, orbit the Milky Way in a wide arc and exert a gravitational pull that tugs unevenly on the outer disk as they pass. This tidal torque is a leading explanation for the warp, and the geometry broadly fits. The outer disk bends more strongly in the direction of the Magellanic Cloud's influence, but there may be other contributions. The dark matter halo surrounding the disk may not be perfectly aligned with the disk's own plane, and a misaligned halo exerts a torque that could tilt the disk's outer edge over time. Streams of intergalactic gas falling onto the galaxy from outside carry momentum and could push the outer disk off its original plane. The warp may be a combination of all these forces, accumulated over billions of years of gravitational exchange with the galaxy's environment, not the scar of a single event, but the slow expression of everything the galaxy has experienced since its disk first settled into rotation. A Cepheid variable star in the outer warped disk pulses steadily in the dark. It swells and contracts over days or weeks, its brightness rising and falling in a rhythm as reliable as a clock, its luminosity determined precisely by that rhythm, its distance calculable the moment the period is measured. Hundreds of these stars have been found in the outer disk, their distances mapped in 3 dimensions, Their positions used to trace the curve of the warp, the way a surveyor traces the curve of a road, by placing markers at measured intervals. Each one is a single old star, fusing hydrogen in its core, oscillating under the competing pressures of its own gravity and the outward push of its internal energy, carrying no awareness of the galaxy whose architecture it is being used to trace. Each one sits in the outer disk, in whatever phase its orbit has brought it to, rising above or below the nominal plane by a distance measured in hundreds or thousands of light years. A small marker in an immense structure that bends so gradually the deviation is imperceptible at any single point along the arc, but cumulative and undeniable across the full breadth of the outer galaxy. The warp means the disk does not end cleanly. The outer edge is already uncertain. There is no sharp boundary where the disk simply stops. The stellar density thins with increasing distance from the center in a gradual exponential decline, and the gas thins as well, and the star-forming regions grow sparser and more widely separated until eventually there are no more HI regions, no more young blue stars, only old stars drifting slowly in orbits that carry them through a region where the disk's identity is dissolving into the halo. The warp adds a further ambiguity. The outer edge is not only thin, but displaced, lifted or lowered by thousands of light years from the plane where the inner disk resides, so that defining where the disk ends and the halo begins requires choosing a criterion and accepting that the boundary is as much a question of definition as a physical fact. The dust in the outer disk also thins. This thinning matters in a quiet way. The dust that blocks light in the inner disk, that walls off the galactic center from any optical observation, that carves the Milky Way's visual band into bright regions and dark rifts, that dust is concentrated where the gas is concentrated, in the star-forming inner and middle disk. In the outer disk, past the last molecular clouds and the last great star-forming complexes, the dust clears. The sky in the outer disk is less obstructed. Light passes more freely. Looking outward from a star in the outer disk, the view into the surrounding universe would be relatively unobscured, a cleaner window than the one available from the sun's position deeper in the populated middle disk. But there is less to see nearby. The outer disk is quieter. The star forming is largely over. The clusters and nebulas and glowing HI regions that populate the inner arms are not here in the same numbers. What remains is a slow, thin sprinkling of older stars in wide orbits, drifting apart as the disk's grip on them weakens with distance from the center's gravitational concentration. The magnetic field persists into the outer disk. It is weaker there, spread across a larger volume, less structured than the field in the star-forming arms where supernova remnants and the motions of ionized gas continually stir and amplify it. But it does not vanish. It threads outward along the spiral arms as they extend into the outer galaxy, gradually weakening, gradually disordering, until in the outermost regions it merges with the general halo field, and the distinction between disk field and halo field becomes as ambiguous as the distinction between disk and halo itself. A cosmic ray particle drifting in the outer disk has farther to travel before the field can turn it and send it back inward. The confinement is weaker. Some fraction of the particles born in the arms accelerated in the hot, bright inner galaxy, and then diffusing outward through the disk on their long spiraling paths, escape into the halo before the field can redirect them, carrying energy from the disk out into the surrounding space. A slow leaking of the disk's vitality into the wider volume the galaxy inhabits. The interstellar medium in the outer disk has a different chemistry from the inner disk. In the inner parts where stars have been forming and dying for 10 billion years, the gas is enriched with the elements produced in those stars and expelled in their deaths: carbon, oxygen, nitrogen, silicone, iron, and dozens of others, manufactured in stellar interiors and broadcast into the surrounding medium when stars shed their outer layers or explode. This enrichment, this slow accumulation of heavy elements in the gas over successive stellar generations, is less advanced in the outer disk, where star formation has been slower, the stellar population thinner, the cycling of material through stellar births and deaths less intense. The gas there is more pristine, closer in composition to the original hydrogen and helium that filled the galaxy when it was young, a long gradient of chemical poverty extending from the rich inner disk outward to the outer edge, where the interstellar medium most closely resembles the early universe's composition. This gradient has been measured through the spectra of HI regions at different galactocentric distances, through the abundances of young stars at various radii, and it reveals in chemical terms the story of how enrichment spread outward from the active center across the disk over time. The scale of the disk, held quietly in mind, is worth dwelling on. From the Sun, the center of the galaxy is roughly 26,000 light years away. Light leaving the center now would take 26,000 years to arrive. The far side of the disk is almost twice as far. The full width of the visible disk, 100,000 light years, is a distance so large that the fastest spacecraft ever launched by human hands would need roughly 2 billion years to cross it, moving at roughly 17 kilometers per second, the speed of Voyager 1 drifting outward through the edges of the solar system. And within that vast disk, the Sun sits at one point in its orbit, completing one full circuit in somewhere between 225 and 250 million years, a duration sometimes called a cosmic year. In the time since the Sun was last at its present position relative to the galaxy, the continents of Earth have rearranged themselves. The dinosaurs have appeared and vanished, and all of recorded human history has elapsed many thousands of times over. The Sun is not old in galactic terms. It is middle-aged, perhaps slightly past its middle. It has completed no more than 20 of these great circuits since it formed, drifting always at roughly 220 kilometers per second through its almost circular orbit in the middle disk. There is something deeply settled in that orbit. It is not spiral-shaped, not markedly elliptical. It stays within a relatively narrow range of galactocentric distances, drifting inward and outward by only a few thousand light years over the course of each circuit, bobbing gently above and below the midplane as the disk's own gravitational sheet periodically pulls it back toward the center of the thin layer. The midplane crossing takes tens of millions of years. The full bob, up, back, down, back, takes roughly 60 to 70 million years, a rhythm that has been proposed as a potential influence on the geological record, a slow cosmic metronome ticking through the layers of ancient rock. The evidence for any such connection is not conclusive, and the disk's gravitational structure is complex enough that the simple picture of regular oscillation is a rough approximation at best. But the orbital rhythm is real. The disk holds the Sun in a gentle, predictable gravitational grip, carrying it in a circuit so large and so slow that no instrument built on Earth could feel the curvature of the path, only infer it from decades of careful measurement of stellar positions and motions. The thick disk, drifting above and below the thin disk's active layer, is quieter now than it was when it formed. Those old stars, metal poor, alpha rich, in orbits slightly more inclined and slightly more eccentric than the younger thin disk stars, move through the same space as the younger population, but sample it differently, passing through higher latitudes, spending more of their time above the midplane, encountering the warm and hot phases of the interstellar medium more often than the cold, dense clouds concentrated near the plane. They no longer form new stars from the gas they pass through. They are too old and too isolated for that. They drift. They have been drifting for 8 billion years, 10 billion years, moving through a disk that has changed around them, watching its active layer grow richer and more structured while their own population remains unchanged, their chemical signatures preserved, their orbits only slightly altered by occasional gravitational encounters over the vast span of years since they formed. They are the disk's memory of its own early self, still present, still moving, still carrying in their spectra the signature of a time when the galaxy burned faster and hotter than it does now. The dust lane in an edge-on galaxy. The thin, bright smear of stars and gas and dust drawn across the dark seam at its equator. The vast, slow S-curve of the warped outer edge, invisible to the eye, visible only to the patient accumulation of radio observations and photometric surveys and parallax measurements gathered over decades. The hot invisible bubbles carved by ancient explosions, the cosmic ray particles threading their long magnetic paths through the disk, the old thick disk stars drifting above the plane in chemical silence, all of it laid out in a structure so flat relative to its breadth that seen from the right distance and the right angle, it would resolve into exactly that single bright line, bisecting the dark, a line that from Earth, seen from within, becomes the whole arch of the Milky Way overhead on a clear night, the galaxy turning slowly on its axis, carrying everything within it in a vast concentric drift that has continued without interruption for nearly 10 billion years. The outer disk curves away into the dark. It does not end so much as it dissolves, the stars thinning, the gas thinning, the dust clearing, the magnetic field weakening, the last Cepheids marking the last measurable distances before the stellar population drops below what any survey can reliably trace. The warp carries the outer edge thousands of light years above and below the nominal plane, tilted by the patient gravitational persuasion of companions the galaxy has been drawing toward itself across enormous distances over enormous time. Beyond the last traced stars, the disk gives way to something wider and more diffuse, a space that is no longer the disk and not yet anything else. A threshold, gradual and unmarked, where the flat spinning structure of the galaxy's active self opens into the vast encompassing quiet of everything surrounding it. The disk persists inward, still turning, still dense with stars and gas, and the continuous slow work of stellar generations replacing themselves. It will turn for a long time yet, long after the last molecular cloud in the outer arms has been consumed or dispersed, long after the cosmic ray particles currently spiraling through the field have escaped, and long after the last record of any particular supernova's contribution to the ISM's chemistry has been erased by the mixing of 10,000 subsequent generations, the inner disk will still be rotating, its spiral arms still rotating through the stellar gas, still compressing and releasing, still building stars from the same material that has been cycling through this process since the galaxy was young. The outer edge curves quietly in the dark, tilted from the plane by a few thousand light years, barely perceptible in the full breadth of the structure. A slow lean, accumulated over billions of years, and continuing still, carrying the disk's far edge gently away from flat. A globular cluster hangs in the outer dark, Far above the galactic plane, visible from Earth on a clear autumn night as a faint and formless smudge just at the limit of the naked eye. Through a telescope, it resolves slowly, not all at once, but gradually as the eye adjusts and the aperture gathers more light, into a sphere of points, each one a star, packed so tightly at the center that they blur together into a single soft glow and only thin out toward the edges into individual lights spaced across the dark. The sphere is dense and ancient and quietly radiant, a thing that has been orbiting the galaxy since long before the sun existed. To look at it is to look at something formed when the universe was less than 1 billion years old, when the first great clouds of gas were falling inward, and the Milky Way was not yet a disk, not yet a spiral, but only a collapsing envelope of primordial material finding its shape. These clusters number in the hundreds, scattered through the halo in a roughly spherical arrangement, extending in some cases to distances of 130,000 light-years from the galactic center. They are among the oldest surviving structures in the galaxy. Most of them contain hundreds of thousands of stars, sometimes more, bound together by their mutual gravity into a shape that has maintained itself across billions of years of slow orbital motion. They do not follow the flat disk. They do not trace the spiral arms. They travel in long looping paths that carry them up through the disk, across the outer halo, and back again on timescales that stretch across hundreds of millions of years, arcs so wide and slow that the full extent of a single orbit has never been witnessed by any mind. The light from a globular cluster, even through a telescope, is the light of a single moment in an 11 billion year continuity. The stars within it are not isolated. They are packed close enough that in the densest regions near the core, the typical distance between neighboring stars shrinks to fractions of what separates the sun from its nearest neighbors. Some of these stars have interacted, exchanged mass, even merged. At the centers of the largest clusters, there may be intermediate mass black holes, objects more massive than anything a single star could become, but smaller than the supermassive ones anchoring the cores of galaxies. Their presence still debated, their evidence read in the faint orbital velocities of the stars moving around them in the crowded dark. The clusters divide into two broad families. Some are metal poor, carrying in their spectra the chemical signature of very early times, almost no iron, almost no calcium, trace amounts of elements heavier than hydrogen and helium, because when they formed the universe had not yet run through enough generations of stellar death and explosion to enrich the gas with much of anything beyond what the Big Bang produced. These oldest clusters orbit in wide, eccentric paths through the halo and are likely the remnants of the proto-galactic cloud from which the Milky Way assembled. The others, slightly less ancient and richer in metals, are associated with the central bulge and travel in tighter, more organized orbits closer to the galactic plane. Their different chemistries and orbital histories trace two different origins, two different eras, laid on top of one another in the same slow-moving halo. A single star within a globular cluster has lived its entire existence in conditions almost nothing like the sun's. The stars are old enough that the most massive ones burned out long ago. What remains are the survivors, low-mass stars that burn slowly and steadily, red giants that have expanded and cooled, white dwarfs, and the faint embers of stars that were never very bright to begin with. The cluster has evolved, grown older, grown quieter, lost its loud and energetic youth to supernovae that swept through it in the first few 100 million years of its existence. What endures is a community of slow, old, patient lights, orbiting one another and orbiting the galaxy together, on paths laid down before the solar system was dust. Across the halo, other structures mark the long history of smaller things that came too close and were pulled apart. Not all the material in the outer galaxy arrived neatly. Small galaxies, dwarf spheroidals, dwarf irregulars, satellite systems barely large enough to hold themselves together, have been orbiting the Milky Way for billions of years, and some of them have wandered too close. When a small object passes within reach of a massive one, the near side of the smaller body feels a stronger gravitational pull than the far side. That difference, small at first and growing as the orbit decays, is enough to draw the smaller system out into a long, thin filament of stars. Over hundreds of millions of years, the small galaxy ceases to be a compact object and becomes instead a stream, a river of stars, threading through the halo along the path its parent once traveled. These streams are ancient and numerous. The halo is filled with them, overlapping and crossing one another in a slow tangle of stellar history that no eye can see directly, but that surveys of millions of faint stars have slowly made legible. One of them arcs around the entire sky. It was traced first through subtle patterns in the distribution of red giants detected in photometric surveys, not visible as a band of light, but detectable as a statistical weight, a place where slightly more stars of a particular color and luminosity appeared than the smooth halo model predicted. Followed and extended across the full sphere of the sky, it resolved into the remnant of a small galaxy, a dwarf spheroidal found in the 1990s on the far side of the galactic center, approximately 70,000 light-years away, on the opposite side of the Milky Way from the Sun. That galaxy, the Sagittarius dwarf, is still there. It has not been fully consumed, but it is being unmade, slowly and continuously, over billions of years of repeated orbital passages. Each time it swings close to the Milky Way, more of its stars are peeled away and added to the stream. The core that remains is a loosened, diffuse thing, much diminished from what it once was, still orbiting but fraying further with each passage. The stream it has deposited wraps at least once around the full circuit of the halo, a ghostly remnant of orbital history stretched across a volume of space far larger than the visible disk of the galaxy. That stream has been used as a measuring instrument. The shape of a tidal stream, how quickly it fans out, whether it curves or stays straight, how its leading edge precesses relative to its trailing edge, carries information about the gravitational field through which it has traveled. The Milky Way's dark matter halo is not something that can be mapped directly, but a stream that has spent billions of years threading through it carries the gravitational imprint of everything it encountered. By modeling the observed stream against different assumed halo shapes, researchers have worked to read that imprint, whether the halo is spherical or somewhat flattened like a lens, or elongated along an axis. These possibilities produce subtly different predictions for how the stream should appear, and the debate over what the observations best match is ongoing. The answer matters because the shape of the dark matter halo records the history of how the galaxy assembled, and no measurement of it is simple. Other streams cross the sky in shorter arcs. Some are thin and tight, so thin that they likely came from globular clusters rather than dwarf galaxies, a single cluster slowly dissolving under the Milky Way's tidal field, leaving behind a narrow thread of stars spread along its former orbit. These streams trace nearly perfect arcs, smooth and regular, because a globular cluster is a relatively simple dynamical system, and its dissolution is correspondingly ordered. One of these thin streams stretches across roughly a third of the sky, its stars so uniformly distributed along the arc and so cleanly separated from the background that when researchers first mapped it in photometric survey data, it appeared almost geometrically precise, a line drawn through the halo, steady and faint, carrying the stars of a cluster that no longer exists as a cluster. The stars remain, the cluster is gone. What persists is only the path, marked in light. The halo stars that do not belong to streams or clusters move differently from disk stars, where the sun traces a nearly circular orbit around the galactic center, staying close to the plane, completing one circuit in roughly 225 million years. The old halo stars follow paths that are eccentric and tilted. Some travel in orbits nearly perpendicular to the disk, arcing far above and below the galactic plane before swinging back through. Some travel in the opposite direction from the general rotation of the galaxy, retrograde orbits, moving against the slow spin of the disk, carrying information in their velocities about the events that place them there. They are not products of the disk. They formed before the disk existed, in the proto-galactic halo, or in the small satellite galaxies that merged with the Milky Way in its early history and are now dissolved into it beyond recognition. The oldest of these stars are chemically almost empty in the way that the early universe was almost empty, no heavy elements to speak of, because at the time they formed the only way to make elements heavier than lithium was inside a star, and the very first stars had only just begun to live and die. When the first massive stars exploded as supernovae, they scattered the first traces of heavier elements into the surrounding gas. The stars that formed from that enriched gas carry those elements in their atmospheres even now. At the most extreme end, where iron abundances fall to 100,000th of the sun's or lower, these stars are essentially primordial, formed from gas that had been through perhaps one or two generations of stellar processing, carrying the chemical fingerprints of the very first supernovae. They are old enough that whatever population 3 stars, the hypothetical first generation, massive and metal-free, died before them, the remnant chemistry of those deaths is what built these ancient survivors. To find a star like that and read its spectrum is to read a message from an era no longer directly accessible. The first stars themselves are gone, their light too old and too shifted by cosmic expansion to observe in any ordinary way. But the chemistry they printed into the gas they enriched survived in the stars that came after, and those stars are still here, drifting through the halo in retrograde paths, cold and old and carrying a record no other instrument can match. The spectrum of a single ancient halo star contains, in compressed form, the chemistry of the early universe, the yields of the first supernovae, the conditions under which the first nucleosynthesis beyond the Big Bang proceeded, the proportions of elements whose ratios depend on the masses and explosion energies of progenitors that no longer exist anywhere as intact objects. The outer reaches of the visible disk thin and grow quiet at distances roughly 60,000 light-years from the center and beyond. The spiral arms, so clearly defined at closer radii in the distributions of young blue stars and glowing ionized gas clouds, lose their coherence. Star-forming regions grow sparse. Individual molecular clouds appear widely separated without the continuity that marks the dense inner arms. The gas thins, the density of young stars falls, the last traceable Cepheid variable stars, bright pulsating supergiants, whose luminosities and pulsation periods follow a tight enough relationship to serve as reliable distance markers, appear at distances that mark an uncertain boundary beyond which the disk seems to fade into something less structured, less definite. That boundary is not clean. The the disk does not end so much as cease to be clearly distinguishable from the halo it merges into. A survey of Cepheids from a wide-field infrared telescope completed in the last decade extended the traceable disk to distances that pushed the known edge further out and confirmed the slow S-shaped warp that earlier radio surveys had detected in the distribution of cold neutral hydrogen gas. At the outer reaches, the disk curves, one side bending upward by several thousand light years, the other side curving downward. The warp is not dramatic from within. Seen from outside, it would appear as a gentle lean, a slow deviation from flatness accumulated over billions of years, likely driven in part by the gravitational torque of the large and small Magellanic Clouds pulling on the outer disk from their current positions in the halo. The Magellanic Clouds themselves are satellite galaxies, the largest and most nearby of the Milky Way's companions, visible from the southern hemisphere as two detached patches of the Milky Way, bright enough to cast faint shadows on the darkest nights. The Large Magellanic Cloud contains several billion stars and carries active star formation regions, including the Tarantula Nebula, a region of ionized gas and embedded young star clusters, so large and luminous that if it were placed at the distance of the Orion Nebula, it would cast visible shadows at night and be bright enough to read by. These two companion galaxies are probably on a first or second passage near the Milky Way, their interaction with the disk still early, their eventual fate, whether they will merge into the galaxy over billions of years or escape on a hyperbolic trajectory, dependent on poorly constrained measurements of their total velocities relative to the Milky Way's mass. Beyond the visible disk, beyond even the sparse outer reaches of traceable stars, the halo continues. Its stars thin gradually into the distance until they become too few and too faint to map statistically with confidence. At distances of 100,000 light-years or more, individual globular clusters appear as isolated outposts, the most remote known ones hanging at distances that place them well beyond the visible disk's edge, orbiting in vast looping paths that carry them through a region so diffuse that the gap between stars can stretch to thousands of light years. The halo at these distances is nearly empty of light, but it is not nearly empty of mass. The evidence for this comes from many directions. The rotation curve of the Milky Way, the relationship between how fast stars and gas orbit the center and how far they are from it, stays nearly flat at large radii, rather than declining as it would if the visible disk and bulge contained all the mass. In a system where light traced mass, orbital speeds should fall with increasing distance from the center, the way planets in the outer solar system orbit more slowly than inner ones. Instead, the speeds stay nearly constant, implying that additional mass exists at radii beyond the visible disk, distributed in a way that extends the gravitational pull outward. The mass is there, the light is not. The same inference emerges from the kinematics of the satellite galaxies and globular clusters. Their orbital velocities, their total energies, the spread of their velocities at different distances, all of these require a gravitational field deeper and more extended than visible matter alone can produce. The most distant tracers of the Milky Way's potential, halo stars caught at the very limits of their bound orbits, carry velocity information that, when combined with models of the halo's mass distribution, point to a total mass for the galaxy several times larger than the mass in stars and gas. The additional mass is dark. It does not emit, it does not absorb, it does not scatter. Its presence is known only through the orbits it shapes. This dark matter halo is inferred to extend far beyond the visible galaxy, to a virial radius somewhere between 600,000 and 900,000 light years, a sphere encompassing the visible disk, the stellar halo, all the globular clusters, all the stellar streams, and the Magellanic Clouds. Within that sphere, models place between roughly 800 billion and 1.5 trillion solar masses of dark material. The visible galaxy, all its stars, all its gas, all its dust, all its stellar remnants contributes less than a fifth of that total. Everything that has been traced in this long passage, from the central plasma ring outward through the bulge, the spiral arms, the disk, and into the halo, represents only the luminous surface of a structure, most of whose substance is invisible. The particle nature of this dark matter remains unknown. The leading ideas include particles that interact with ordinary matter only through gravity and the weak nuclear force, weakly interacting massive particles, which would have been produced in the early universe and would be moving slowly enough by now to cluster gravitationally into halos of the observed kind. Other ideas include axions, particles initially proposed to solve a separate problem in particle physics and later recognized as viable dark matter candidates because of their extremely small mass and negligible interactions with light. Stereoneutrinos have been proposed. Primordial black holes, formed in the first seconds of the universe before stars existed, have been proposed. Experiments have searched for all of these possibilities with increasing sensitivity. None have produced a confirmed detection. The dark matter persists as an inference, well supported and wide-reaching in its implications, but not yet a thing that has been touched, captured, or identified. There is something very old about that situation. For most of human history, the Milky Way was not known to be a galaxy, was not known to be a structure at all, only a band of light across the night sky whose nature was uncertain. The sun's position within it was unknown. The existence of other galaxies was disputed until less than a century ago. The spiral arms were not mapped until the 1950s. The galactic bar was not confirmed until the 1990s. The stellar streams threading the halo were not detected until large photometric surveys began accumulating the statistical precision to find them. The dark matter halo, the most massive component of the entire structure, is known only from its gravitational signature. At each stage, what was visible turned out to be a small fraction of what was present. The pattern has repeated so reliably that it functions now as a kind of expectation that the luminous, the detectable, the countable, will always be nested inside something larger and less immediately apparent. In the halo, on a slow retrograde orbit that carries it far above the galactic plane, a single old star drifts through the dark. It is a red giant now, expanded and cooled from whatever it was on the main sequence billions of years ago. Its iron content is so low that its spectrum is almost featureless where iron lines should appear, reading like a message from an era before iron was common. It formed in the early galaxy, or in a satellite galaxy long since absorbed. It has completed many orbits since then, far fewer than a disk star of the same age, because its orbit is so large and eccentric that each circuit takes 1 billion years or more. When it swings down through the disk, it passes through in a few tens of millions of years and emerges on the other side. Most of its time is spent in the outer halo, far from any gas, far from any star-forming region, in a silence so complete that the nearest neighboring star may be many light years away. That star knows nothing of the structure it inhabits. It does not know it is in a galaxy, or that the galaxy is barred, or that somewhere far below and ahead of its current position, there is a concentration of 4 million solar masses compressed into a volume no larger than a planetary system, whose presence shaped the early dynamics that built the bulge. The star once passed through. It does not know that the invisible material surrounding it outweighs everything it has ever been near, combined. It moves because it was set moving by the conditions of its birth and by every gravitational encounter since. It burns because the pressure at its core is high enough to fuse hydrogen and then helium into heavier elements. And when it finally exhausts what it can fuse, it will contract and cool and fade over billions of years into a cold, dense remnant, barely luminous, still moving through the halo on the same orbit, slightly altered by tidal forces, carrying its ancient chemistry undisturbed into the very far future. The outer halo is mostly silence, not the dramatic silence of a vacuum sealed against something, but the ordinary silence of a very large space with very few things in it, where the distance between objects is measured in light years, and the dominant presence is the dark matter, which makes no sound and produces no light, and exerts its influence only through the patient geometry of gravitational wells. Embedded in that silence, the globular clusters continue their long orbits. The stellar streams continue their slow dispersal, one revolution of the galaxy at a time, spreading and thinning until the stream's stars are too dilute to detect against the background halo. The satellite galaxies continue their passages, pulling at the outer disk, tugging the warp a fraction further with each circuit, and through all of it, the dark matter halo holds the shape, not actively, not intentionally, but because that is what a gravitational well does. It holds. It is worth pausing here in the outer halo, far from the disk, far from anything illuminated, to consider the full extent of what the galaxy is. At the center, the plasma rings surrounding the black hole, the S-stars in their tight elliptical orbits, the warm torus of gas circling at a distance of a few light years, the molecular zone with its turbulent sea of cold gas and its magnetic fields strong enough to resist collapse. Moving outward, the ancient bulge with its peanut-shaped cross-section, its RR Lyrae stars pulsating steadily through 10 billion years of darkness, its faint chemical gradient from the metal-rich midplane to the more primordial stars high above the disk. The spiral arms with their density waves and their triggered star formation, their glowing ionized gas clouds and their rivers of cold molecular material, their young blue stars blazing at the arm crests and already dying by the time the arm's gas has moved on. The thin disk with its layers of gas and dust, its interstellar medium in multiple simultaneous phases, its cosmic rays threading magnetic field lines for millions of years before escaping upward, the warp at the outer edge, and then the halo, the globular clusters, the streams, the satellite galaxies, the old metal poor stars on their long tilted paths, and the dark matter encompassing everything, 10 times wider than the visible galaxy, containing most of the total mass. That is the Milky Way, not only the band of light across the sky on a dark summer night, not only the flattened disk of stars that edge on galaxies show as a thin bright line bisecting the dark, but this entire three-dimensional structure, most of it invisible, most of its mass unlit, extending to distances so large that even the word galaxy begins to seem too small for what it names. The visible part, the part that produces light, that can be photographed, that has been mapped in optical and radio and infrared surveys over decades of work, is the surface of something deeper, the luminous spiral, the bright arms, the soft glow of the central bulge. All of this is a thin luminous skin over a gravitational body that extends far further and contains far more. In the outer halo, the light from the disk is a soft smear far below. Seen from the distance of the outermost globular clusters, the galaxy's disk would appear as a faint elliptical glow, narrowed by inclination to something like a lens or a flattened egg, its spiral structure too fine to resolve at that distance, its central brightening visible as a slightly warmer core. The arms would not be discernible. The individual stars would not be resolvable. The whole familiar structure, everything from the black hole to the last saphid in the outer disk, would appear as a soft and quiet light, a single object, unremarkable from a distance, one galaxy among the hundreds of billions that fill the observable universe. From that distance, the dark matter halo would be entirely invisible. It would leave no mark on the image. Its presence would be detectable only if one were to measure the orbital velocities of the galaxy's satellite companions, or trace the paths of its globular clusters, or follow the stellar streams long enough to see how they curve. Without those measurements, the halo would be gone from view. The galaxy would look smaller than it is. It would look lighter than it is. It would look from outside like a modest spiral, 100 billion stars, a disk of gas and dust, a barred center, 4 main arms, a halo of old clusters, and nothing more. Most of what the galaxy is would be hidden. Most of what holds it together would be invisible. The light it produces, across all wavelengths, from the gamma ray lobes far above the disk to the radio emission of the neutral hydrogen in the outer arms, represents only a small fraction of the energy available and only a trace of the mass present. The stars, for all their number and all their light, are guests inside a gravitational structure they did not build and cannot see. They move in the paths the dark matter halo defines, cluster where the density waves compress their gas, burn and die, and leave their elements to the next generation of clouds. And in none of this do they interact with the thing that surrounds them. The halo holds this all in place. It held it in place when the first stars formed. It held it in place while the disk assembled and the bar buckled and the spiral arms wound outward. It will hold it in place long after the current generation of stars has exhausted its fuel and the disk grows dim and old and the star formation rate falls towards silence. The dark matter halo, whatever it is, does not age in any ordinary sense. It does not fuse hydrogen. It does not cool and contract. It does not undergo any process that would consume or diminish it over stellar timescales. It persists, and in persisting, it will continue to provide the gravitational architecture within which whatever comes next in the galaxy's long history will take place.